Thank you, Giorgio. And first of all, I want to thank again Arjan Kleij, Professor Arjan Kleij from Barcelona, and Professor Shoubhik from Antwerp, Belgium. And we will start today the first meeting of this 3 days meeting. Every Tuesday we will have a presentation about the CO2. Today about ultrasounds and microwave techniques in organic synthesis next Tuesday, and finally the last Tuesday we will have a day dedicated to the presentation of microalgae for as a source of chemicals and biofuels. So today the day is dedicated to the use of CO2. Particularly, we have the honor to have two speakers who have been working a lot, who are dedicating their research on the use of CO2 from different point of view, but they will describe, of course, in much details their work. We will start with Professor Arjan Kleij from ICIQ of Barcelona, Tarragona actually, and thank you for accepting, both of you, the invitation. Professor Kleij, basically, he got his PhD from University of Utrecht, if I'm not wrong, working on polymers with Professor Van Koten, but then he moved to a company, Avantium, working on polymers again, before starting the postdoc. So he had a break in companies and starting postdoc in Madrid with Professor Mendoza, then in Amsterdam with George Streck, and then he moved in ICIQ as assistant, as research leader, and then as professor in 2011. So besides his career, he's basically has been contributing in several different aspects of catalysis and polymer chemistry. He has been awarded several prizes, including recently the Royal Sociedad Española de Química, the Award for Excellence in Research, in Scientific Excellence. And he is acting as in the advisory board and in the editorial board of several journals dedicated to the different catalysis and sustainability publication. So basically, he has been interested in different aspects of the use, valorization, and use in catalysis of the CO2 for preparing polymers, but not only. So we will have a very unique opportunity to hear directly from him the recent advances in his research. And I thank Arjan again and leave you the stage for sharing your screen and give the presentation, Arjan.
So thank you very much for this kind introduction. I also would like to thank the organizers of this meeting, but also the subsequent meetings, for setting this up and for allowing me to discuss, let's say, part of our research. Some is a little bit more ancient, but I think most of the results are from recent years. And I'm happy to be in this meeting where the focus is on carbon dioxide. And as you probably know, carbon dioxide is a very interesting building block for synthetic chemistry. And hopefully today I can show you what kind of dreams you may be able to realize when considering this carbon feedstock. I slightly changed my title, so there was a couple of different words here. So I will focus on fine chemical and functional polymer development. So the first part will focus on how to utilize carbon dioxide using catalysis and making, let's say, chemical intermediates, functional molecules, and the second part will focus on polymers. Let me see if I can get the laser to work. Well, if that's not the case, you probably can see my cursor anyway. So,
Arjan?
Yes.
You can start the presentation, the slide view. So
sorry,
larger.
Right. I'm too enthusiastic. Here it is.
Thank you.
Right. Okay, I'm all set up. So thank you very much. Again, As I said, carbon dioxide is an interesting building block. But if we want to consider the framework in which we want to use carbon dioxide, then obviously we quickly can discuss the, let's say, the importance of circular economy or circular chemistry. And in this respect, if we want to make the carbon that we emit through CO2 and through other, let's say, waste streams, we want to be able to recycle that carbon into useful molecules that will retain the carbon for a longer period of time. And in that way, we can more strictly, let's say, control the carbon economy. As I said, recycling of waste is very important, especially if you can make it economic. So this needs to be made economical, otherwise it has little commercial value. So recycling of waste into value-added products is something that we have been working on for quite some time. You will see some examples popping up during this presentation. A third reason why we are interested in the recycling of CO2 and waste in general is that in some cases, you can recycle that waste into new types of plastics that are based on renewables, and in that way, you should be able to address some of the problems that are out there, considering the pollution that we have currently affecting our societies. I think everybody recognizes the problem of plastic pollution, and this is something that we have to address in the decades to come. A couple of terms that are very important in the design of new plastics, that is recycling, and if that is not possible, upcycling. So can we recycle the atoms that are present in waste plastics into new kinds of products? And also biodegradation is nowadays considered as one of the most important features of newly prepared polymers. Today I will be discussing, I will be discussing the use of catalysis as a way to recycle carbon dioxide. And in this context, from my point of view, there are basically three main areas of catalytic recycling of carbon dioxide. The first one basically focuses on reductive coupling reactions. So what is meant by that? It means that you add to your carbon dioxide electrons, and in a number of cases also protons, and thereby you change the oxidation state of the carbon center. So there are simple examples like formamides, alkylamines, and so on, where the oxidation state of the product is different than what you had in the, let's say, carbon dioxide, where the oxidation state is +4. The second related field is this is energy storage. So basically what you do, you also use energy and protons and electrons in order to produce molecules that are considered nowadays as, well, biofuels, if you like, formic acid, methanol, methane. And therefore, you also change the oxidation state to +2, -2, and -4 in these respective cases. The key, however, here is reversibility. So if you want to use a catalyst that can, let's say, store energy in the form of hydrogen, for instance, producing formic acid, methanol, or any other molecule, then of course you want to get that energy out at the moment that you want to use it. So you need a catalyst that can actually do both. Then third, major area is the area of non-reductive coupling reactions. So that is basically our expertise. And what is mostly important about those kind of, let's say, transformations is that the formal oxidation state of the carbon center in CO2 does not change when you consider the final product. And examples of this are basically organic carbonates, either cyclic, linear, or poly, and carbamates and other types of molecules like ureas. This is still and has been our vision in CO2 catalysis. So when we want to make use of CO2, we want to store that into molecules that are potentially useful for other types of applications. And we have chosen, or we chose basically several years ago, let's say cyclic carbonates as a useful way of utilizing catalysts and to be able to design molecules that are potentially useful. Not only cyclic carbonates, but also polycarbonates, as shown over here, are potentially useful. And in the second part of my presentation, I will come back to the topic of polycarbonates. So we use catalysis, mostly focusing on earth-abundant metals, cheap metals, and organocatalysis to store that CO2 molecule into heterocycles. And then subsequently, we want to make use of those cyclic carbonates that have particular functionalities. And in that way, we can access, let's say, different kinds of transformations where the cyclic carbonate is crucial to get access to fine chemicals, pharmaceuticals, and other types of molecules that are listed over here. So this is sort of a way where we have a circular use of CO2, where we first store CO2 in cyclic carbonates, and then by decarboxylated methods, it is released, but we can recycle that back into cyclic carbonates. So a little bit in an overview what we have been doing over the years. Well, as you may know, cyclic carbonates and other organic carbonates like linear carbonates and polycarbonates have many applications. I'm just showing you a couple of those. So electrolyte solvents, as probably everyone has a, let's say, a phone or a laptop that's typically powered by a lithium-ion battery, and lithium-ion batteries typically contain electrolyte solvents, and that's a huge potential application of these cyclic, essentially cyclic carbonates. Biodegradable materials, that's another area of, let's say, increasing interest of the scientific community. And related to that is a little bit the topic where other types of polymers are being formed through, let's say, cyclic carbonate-based molecules. So these are just foams, as you can see, and those foams are related to polyurethanes. And the topic of isocyanate-free polyurethanes is a very active field now, where cyclic carbonates play an important role. The last thing that I want to address is the use of cyclic carbonates in fine chemical or pharmaceutical synthesis. So this is just one example of a pharmaceutical that you can make from CO2. This is called Co2 and we reported several years ago how you can, let's say, convert CO2 in a number of steps. I think 3 steps. Into this drug molecule. So where do we get our inspiration? Well, as in a lot of examples where I think 3 steps into this drug inspiration to be found in nature. So these are just 4 selected examples of cyclic carbonate molecules here highlighted in blue-purple or purple-blue. But as you can see from all these 4 examples, that the complexity and substitution degree is something that is quite elusive for synthetic chemists. So the question that we basically asked ourselves at a particular point in time is how to create similar kind of complexity using synthetic approaches. Yeah, so these compounds are can be found in nature, but how can we design synthetic methodologies that will allow us to basically level or go beyond the complexity that we see over here? Well, to do that, we started our research using epoxides. So epoxides and CO2 can be coupled to form a cyclic carbonate, and this is well-established chemistry in general. So you basically use a Lewis acid, you activate the Lewis, via coordination, the epoxide for a nucleophilic ring opening, and then you produce this reactive intermediate. And this reactive intermediate, if you control the reactivity of that sufficiently well, then it may insert CO2. You've formed this hemicarbonate, and now we can cyclize onto that carbon center and expelling the nucleophile while forming the cyclic carbonate. Of course, there are some parasitic reactions. You might be able to form here a polyether or a polycarbonate or anything that goes in between. But by designing your catalyst well, you can control the chemoselectivity of this reaction. However, there are challenges, and there are still challenges out there, which are related to the creation of highly functional carbonates or highly substituted carbonates, larger ring heterocycles. So here you see a 5-membered cyclic carbonate, but how can you design methods that will allow us to access 6, 7, and even higher order ring carbonates, and also the lower reactivity of the substituted oxytanes and epoxides has been a problem, has been a challenge for quite some years. So why would you want to make substituted carbonates? Well, if we consider the general setup, the general scheme for making a cyclic carbonate, we make use of an alkene, then we can, of course, prepare in a very simple way an epoxide, and that epoxide then reacts to the cyclic carbonate using a suitable catalyst and CO2. So in that sense, it's important to consider the reactivity and the availability of the precursors. So if you want to introduce, like in this particular example, sterics, or you want to introduce, let's say, a more functional backbone, then of course you need to be able to address that with catalysts that can convert, let's say, the respective epoxides into carbonates. And even if you want to increase further the substitution degree, as you see over here, so this is, let's say, has as a precursor a tri-substituted epoxide. So those are considered to be quite lethargic in terms of reactivity, so it's difficult to convert them. And you have to use very, very potent catalysts and typically very high reaction temperatures and pressures. So the reason why we still want to, let's say, develop methodologies is that these kind of conversions tend to be more difficult to perform. Another reason is, of course, the functionality that you can introduce into a carbonate. There are various ways of doing so, and we have been interested for several years in vinyl cyclic carbonates, as you see over here. This is an example. So this structure has a lot of potential in synthetic chemistry, and we are not the only ones working in this field, but we have been able to design interesting stereoselective, let's say, transformations where we have been able to produce, for instance, allylic compounds of this type, where we have an allylic amine being formed, or an allylic sulfone, as you can see over here, or maybe this example where we were able to make use of water as a nucleophile and to produce these 1,4-butene diols. In a more, let's say, slightly more challenging conversion, we have also been able to design compounds, unusual compounds with quaternary carbon centers that are highly functional, with an aldehyde, a vinyl group, an allylic group, and a substituted aromatic group. So the reason why we want to use that functionality is that we can access a lot of these interesting transformations. So functionality is important to consider in the design of new cyclic carbonates. Well, you can take it one step further in terms of complexity. So you can use this vinyl carbonate also for chiral conversion. So basically what we do here, we decarboxylate and we produce an intermediate halal palladium species that, if properly mastered by the ligands that we have, we can form chiral compounds, as you see over here. So this is a chiral allylic amine. Here we have just another version of that, but you can also make sulfones. And we have been involved in mechanistic studies as well to understand and unravel the details of this manifold. So this is just another example. Then, just to show you one more example, so if you want to change then the functionality, it's not so difficult to do so. So here, this is an alkyne-based cyclic carbonate, and that alkyne group we can also activate. But then, of course, we need a different metal, in this case, copper, and then we can do propygylic substitution reactions, as you see over here. Or we can make, more specifically, this 1,2-diborylated diene, also under the influence of copper catalysis. And by changing a little bit the nature of this cyclic carbonate, we can access these tetrasubstituted silylated alpha adeninols. So this is just to show you that the type of functionality that you have in your molecule can be extremely important for the subsequent synthetic potential of those cyclic carbonates. Well, a little bit back to the main theme, and that is how to make a cyclic carbonate. As I've shown you, typically what people use nowadays is an epoxide and CO2, and we have a Lewis acid and a nucleophile. And then basically we go through this sequence of steps. So this is just, in short, how you can make then your cyclic carbonate. And please pay attention to the colored oxygen atom, as you can see over here. It is incorporated into this heterocycle. Well, we set out to do something different, and by making use of, let's say, pendant functionality in the, let's say, epoxide. So here we have basically an epoxyamine that is almost equally true for epoxy alcohols. We can make use of that amine, and we can activate CO2 in the presence of a suitable Lewis acid and produce here this hemicarbamate species that then takes the role of a nucleophile and can attack this epoxide in a nucleophilic or let's say intramolecular nucleophilic reaction. And in this way, we also make a heterocycle. But as I said before, if we look at the color coding in this molecule, now we're seeing this green-colored heteroatom being incorporated into the structure. And this is essentially a different product than you would get from a standard manifold. So that allows us to do chemistry, which is different. And moreover, in a number of cases, we don't need this halide as a nucleophile, so we can do halide-free synthesis, which is also a plus if you take sustainability into account. Well, to take that a little bit further here, I'm just showing you a few examples, what types of molecules you can make using epoxyamines and epoxy alcohols. Yeah, so we have some carbonates here, but also more relevant type of compounds. So this is called tolaxetone. This is a drug molecule. It's actually sold in the market. You can make that molecule at room temperature under halide-free conditions, and by changing basically the groups that you have on your nitrogen center and the groups that you have on your, let's say, or near your alcohol, you can actually design a whole set of let's say, pharmaceutically relevant building blocks. Well, how does it work? We have several, let's say, mechanistic control reactions and insights. So we took this chiral compound, this is commercially available, and we took our catalyst and CO2 and we made this intermediate molecule. So we know that in this transformation, we have a very high diastereoselectivity, but we actually had to benzylate it in order to be able to crystallize. And what we saw formally is that we invert the, let's say, configuration at that carbon center. And that gave us proof for an intermolecular, let's say, nucleophilic attack in a formal SN2 reaction. And that's exactly what you would predict from this intermediate. We have further evidence. I won't go through all the evidence, but I think this is quite an interesting, let's say, way of proving that this is indeed the mechanism that is ongoing. So we deuterated this glycerol at this position, monodeuteration. And of course, if this would go through a similar type of intermediate as you see over here, we would form this carbonate with the deuterium basically residing outside the, let's say, the carbonate ring. And this is exactly what we see. So we see quantitative deuteration at this position and no deuteration on, let's say, at the ring positions. So this is further proof for this mechanism. We have done much more. I'd just like to show you this slide where we have basically set up the entire scheme for epoxy alcohol conversion into cyclic carbonate. So this is just, of course, glycerol. And we know from the first step that despite of having a lot of examples in the literature of epoxide coordination and epoxide activation for cyclic carbonate synthesis, we saw that in this particular manifold, in order to advance to the cyclic carbonate structure, we need to coordinate the alcohol group. And in that way, what we do, we activate this alcohol for deprotonation, and then one of the oxygen arms of this amino triphenolate structure is basically acting as a basic residue and deprotonating this alcohol. So this is by the way, the X-ray structure of our, let's say, starting complex. Then, of course, we have an epoxy alcohol deprotonated, which now acts as a good nucleophile. It can activate CO2, as you see over here. And this intermediate now is a little bit complex, as you can see. So there's also a water molecule involved. But this intermediate is now set up to do an SN2 reaction on that carbon center of the oxirane, forming finally the product that is shown over here, and then decomplexation is the final step. So the interesting thing is that we follow this reaction by in situ operando infrared spectroscopy, more specifically ATR-IR, in collaboration with one of my colleagues here at the institution at that time. And we can actually monitor the formation of that species. So this species is something that you can see under catalytic conditions, giving this very specific, let's say, absorption in the infrared. And then when we cross-check with DFT, we see that this actually makes very good, let's say, yeah, it compares very, very well with the experimental value. So we know for sure that this species is indeed being formed, and we can monitor that in situ. If we then, by DFT, look at the calculated barrier for this process, which is about 24.6, that also relates quite well with the experimentally determined barrier of 23.3. And just as a comparison, for comparison, the uncatalyzed reaction is at 36.0 approximately. So it shows you very nicely that this catalyst is indeed doing a very good job. At that time, we also asked ourselves, simply because the direct coupling of tetra-substituted epoxides and CO2 had not been reported, we thought, can we design other approaches where we can make highly substituted carbonates? And so we considered that the Payne rearrangement actually gives us a very good idea how to do that. So the Payne rearrangement is the isomerization under basic conditions of this epoxy alcohol towards this epoxy alcohol. You see that basically formally, apart from the interchanging, the colors, we also see that the R group now switches from being here a ring substituent to a acyclic substituent. So we considered that that principle is actually also potentially applicable to carbonates. So we designed a method where we can use an epoxy alcohol and using a suitable catalyst in the presence of CO2, we should be able to form this intermediate. Now, I hope a little bit more familiar to you. And then this catalyst, of course, after attack on this carbon center, should still be interacting with that carbonate molecule. Yeah, so this is our first product. And if the catalyst here is a basic amine, then in principle, we should be able to activate that tertiary alcohol for isomerization, for attack onto this carbon center, and basically isomerize this carbonate molecule towards this carbonate molecule. And since both carbonates have distinct reactivity, if we consider the alcohol group, because here we have a tertiary alcohol, here we have a primary alcohol, we can trap the primary alcohol selectively and then drive the equilibrium to the side of what we call the most substituted carbonate product. And this is what we now have doped the Payne type, let's say, domino approach towards cyclic carbonates. So how does it work in practice? Well, you take an epoxy alcohol, you have this kind of substitution, and you take DBU, and DBU is nothing else than this very simple, commercially available and relatively cheap molecule. And this is our protecting agent, yeah, so we acetylate basically the alcohol so that it will not isomerize back to the other carbonate. And in this way, you can do chemistry basically at 45 degrees centigrade with something that we call, at least in the first step, organo catalysis. So then, with that method or that methodology, you can produce molecules that are listed over here. So this is just a selection. But the interesting thing now is that you can design molecules with different functional groups. So here you have an epoxy group and a carbonate group, or you have two, let's say, olefinic groups that are flanked by this carbonate group, or even this bis-epoxy derivative. And you can make these molecules in a remarkable chemoselective and also regioselective fashion. You can take that one step further by making use of this type of epoxy alcohol that also works. Gives a little bit lower yields, since these are more complex type of, let's say, molecules to make. But essentially it works quite well. So we can get up to 78% yield of tetra-substituted cyclic carbonate, either with the free alcohol or with the protected alcohol, depending a little bit on the conditions that we use. So this marks, I think, a very interesting step forward in the formation of cyclic carbonates, while making use of, let's say, epoxides as starting materials and CO2 as the other partnering reagent. Well, we know also how it works. So this is basically our full scheme. We have the epoxy alcohol. We make this intermediate. We form first this product carbonate that then isomerizes to this other carbonate. And then finally, of course, we have to protect this alcohol to prevent this back isomerization. So we typically see here in 723 equilibrium mixture. There are some important things to note. If we do not add DBU or CO2, then we don't see any isomerization. So we don't have classical Payne rearrangement. Yeah, so base catalyzed isomerization. So we both need DBU and CO2 to make this reaction work. And second, if we isolate non-equilibrium mixtures, for instance, 4-6 or 9-1, of these two carbonates, and we subject them to the catalytic conditions, then in both cases we see that we get equilibration to the, let's say, expected 7-3 mixture that we see for a number of these carbonates when we make them. The third control experiment we did was basically using two types of precursors. So here we have a tri-substituted epoxy alcohol, and here monosubstituted. They both differ also in the reactivity of these alcohols, so we have to use some slightly different conditions to activate those, but essentially the rest of the conditions are quite similar. And what we see in both cases, we get exactly the same equilibrium mixture before we protect the, let's say, pendant alcohol. And so this actually proves that this pre-equilibrium is a very important moment during the formation of the final product. So how can we make further, how can we capitalize basically on this reactivity? Well, Chang and Josephine, they considered not the epoxy alcohols, but to insert basically an additional carbon between, let's say, the oxirane and the alcohol unit, as you see over here. So these are basically made from homolytic compounds. And of course, in a very simple setup, you can make 5-membered cyclic carbonates. That's nothing unusual. Here is just a small set of carbonates that we prepared as precursors. But the interesting thing now is that if we make use of this known, let's say, reactivity where we can activate this alcohol group for attack onto this carbonate carbon, now we can also, under very similar conditions, make 6-membered cyclic carbonates in a very selective fashion. You can easily follow these reactions because in the infrared, these carbonates are well separated, as you can see over here. And what we know is that we have to go through this kind of intermediate. We don't see that intermediate by any spectroscopic means. That means that its equilibrium concentration is very, very low. But since we are driving the equilibrium to the side of the protected 6-membered cyclic carbonate, this reaction is actually more than feasible. So we can make, these are just 3 examples, different, let's say, substituted 6-membered cyclic carbonates. We have X-ray proof for one of these. And the essential, let's say, or the essence of most of these transformations is to understand where this reactivity comes from. That is explained over here. So if we take the starting material, the 5-membered cyclic carbonate, we know that we can form the 6-membered cyclic carbonate, so that's kinetically feasible. Here's the barrier in kcals per mole. However, this is thermodynamically, let's say, uphill. So that explains why we are not seeing this species being populated at room temperature when we, let's say, use that carbonate in the presence of DBU and CO2. However, the second step is actually more facile. So we want to protect this alcohol. We can actually do that. So this reaction is not only kinetically feasible, but also thermodynamically. So we go downhill. And this proves very nicely that this is the only product that we see, and we get that also in high yield and at room temperature. Of course, one can question that also this starting material can be acetylated, so why don't we see that? Well, the reason for that is that the kinetic barrier is actually quite high, so that is much higher than the barrier we see for the protection of the 6-membered free alcohol carbonate. And also this compound tends to be a little bit uphill in terms of free energy when we compare that to the 5-membered cyclic carbonate. So this is, I think, a semi-quantitative or reasonably quantitative explanation why we see what we see. Why are these 6-membered cyclic carbonates important? Well, as you may know, they are susceptible towards ring opening polymerization. So these compounds are kinetically stable with thermodynamically typically unstable. So you can, with a suitable nucleophile, ring open that carbonate, and that way you can make a polycarbonate, and that's one of the applications that we also had in mind. But when we used these carbonates in ring opening polymerization, we saw that actually these attempts were not successful, and we basically deprotect the acetyl group, and we go back to the 5-membered cyclic carbonate. And so we had to come up with a different approach, and that's what I will show you on the next slide. So on the next slide, or this one, you see that you can form these 6-membered cyclic carbonates in a different way. And this is just one of our most recent results where we are making use of an homolytic alcohol, as you see, a lytic alcohol that is protected. So this is an OBOC derivative, if you like. And now under suitable photocatalytic conditions, we can form here a radical species. And the way we do that, we make use of this reagent, which is Kumamoto's reagent, where we can easily, under photocatalytic conditions, produce a CH3 radical that adds to this double bond, forming here this benzylic radical. And now by applying suitable conditions, we can do a single electron oxidation and produce here a benzyl cation. This benzyl cation then will react with this O-Boc derivative, or so this O-Boc group, expel isobutylene, and form this cyclic carbonate that you see over here. And these are also potentially ring-opening polymerization monomers. And the important thing to note here is that they have a different substitution to the compounds that I've shown you already. These are just a number of, let's say, compounds we made. We have X-ray analysis of that compound, which I will show you on the next slide. This shows you that we have some degree of substitution here on this carbon, while we are having, of course, standard CF3 group on the other carbon. Well, now we were able to do ring opening polymerization, so this also to show you that these compounds indeed have potential. So if we make use of this particular precursor that under the influence of an N-heterocyclic base, this TBD and benzyl alcohol, these are standard conditions from the literature, we can produce this polymer. So this is a polycarbonate polymer, if you like, where we are having now, well, a moderate molecular weight. But the important thing is that we can do this at room temperature. We have complete regioselectivity in the ring opening, and by differential scanning calorimetry, we see that the TG is about 110. So this is very promising, and I will not be able to go into details, but by variation of these aromatic groups, we can actually get very, very high, let's say, class transition temperatures. This particular species was unreactive in ring opening polymerization. So here I'm showing you the X-ray. So this is the carbonate ring. And as you see, this carbonate carbon is basically blocked from both sides. So there is no way a nucleophilic species here can easily activate this carbonate for ring opening. So this shows you nicely also that a proper design of your six-membered cyclic carbonate is very, very important. Well, as a last example of how you can make use of, let's say, precursors that will allow you to do substrate-controlled CO2 cascades is given over here. So this is recent work from Alla and Shutong, two PhD students in my laboratory, and they make use of propylylic alcohol. So this is a propylylic alcohol. The only thing that is different now compared to the state of the art is that these have different substituents. And specifically, they have this alkyl or this alkanol substituent where this tandem alcohol also serves as a pro-nucleophile. And under suitable conditions, and those are related to the use of a silver salt and a suitable ligand, under reasonably mild conditions, we envisioned that we would first form this alpha achillidine carbonate, which is basically a standard result from the literature. However, by having this nucleophilic or pro-nucleophilic species or a group incorporated into this carbonate, we should be able to rearrange, and this is exactly what we see. So we finally formed this keto carbonate as we have doped it, and these are just a number of examples, successful examples. In total, we have around 26 examples currently, and we're still expanding that as we said, well, as we speak. I'd like to draw the attention to this very bulky elemental group that is also endorsed, and the formation of this, these tri-substituted cyclic carbonates, which some of these have been confirmed by X-ray analysis, and also the formation of this tetrasubstituted cyclic carbonate seems to be feasible based on results that we have obtained a couple of days ago. So I think this shows you that this concept of substrate-controlled CO2 cascades can be extended to other types of, let's say, precursors. Okay, since I have been discussing already a little bit about, let's say, polycarbonates and polymers, now I'd like to switch gears and discuss the reasons why, since about 6 to 7 years, we have become interested in using CO2 also for the formation of polymers. And one of the reasons was actually provided by the increasing, let's say, legislation that nowadays is applicable to the use of BPA, which is this molecule. This is bisphenol A, and as probably some of you are aware of, bisphenol A, together with a suitable precursor, in practice this would translate to DPC, diphenyl carbonate. You can combine these molecules, and by a melt polymerization process, you make this polycarbonate. So this is commercial polycarbonate. It has a lot of interesting applications. Yeah, here are just a couple of pictures what you can do, what kind of applications you can foresee. Here there is a list of applications, medical applications. So in phones, there are coatings that are based on polycarbonates. You can use it for data storage. The automotive, let's say, market benefits from polycarbonate. And to just give you a flavor, this is a multi-billion dollar market. Yeah, this is data from 2020. However, as I said, there is increasing legislation that limits the use of BPA. Countries, for instance, in Europe, like France and Italy, have banned the use of BPA in commercial synthesis, and also other countries in the world, like the United States and in Canada, they no longer allow the use of BPA. So this was for us a reason to step into this chemistry and to see whether we could design different kinds of polycarbonates by making use of renewables. And the type of renewables that we have been interested in are terpenes. Here are just a number of examples. And terpenes, in essence, are incredibly modular in terms of their structural diversity. Typically, terpenes have double bonds, and as I have already shown you, double bonds can be epoxidized, and in most cases selectively, to obtain their epoxides, and the epoxides by themselves are interesting precursors for making carbonates. So we first considered limonene as a very interesting building block, and the reason for that is very simple, because limonene is one of the most available terpenes out there. And it's even commercially viable. So this is a company in the Netherlands, where peel pioneers, where they basically extract essential oils from the peel of citrus fruit, mostly oranges, and that, those essential oils contain mostly D-limonene. Yeah, that is shown over here. So there is basically a circular solution for that type of industrial waste. And to give you an idea of the market size, so this is already data from some years ago, they are able to use 250 million kilograms of that type of waste and to produce a lot of limonene that can be, let's say, applied in many kinds of applications. They're not only using limonene, they're also using other compounds from the peel and applications among fibers and nutrition additives. There are also cleaning products. And they are working with a number of companies, and most of these will probably not be familiar to you, but it's just to show you that there is really a value chain starting from D-limonene on one side and CO2, and to produce something, let's say, that has a commercial value. So we started to work on this, I think, in 2014. Our first paper was published in 2015. Where we are using this limonene oxide. So this is now already the oxide. We can make it or we can buy it. That doesn't matter that much for this example. But with our proven technology using an aluminum catalyst as shown over here, and with a suitable nucleophile, we can now make this polylimonene carbonate. And this polylimonene carbonate, we can control actually quite well. The polymer chain length, also the polymer dispersity, and also the glass transition temperature, which was about 112 degrees. And that actually is very, very near the one that you would get from cyclohexene oxide. So it gave us confidence to further work on this polymer and to see whether we could further extend the, let's say, thermal properties by changing the, let's say, functionality in these polymers. But first, we have done some development. So we scaled up this synthesis to about 1.5 kilogram. This is needed if you want to make this work interesting for commercial partners. And this was to allow process development to functionalize this double bond in many different ways and to see if that could improve, mechanical and let's say optical and thermal properties, especially when we talk about adhesives or coating applications. Those were the most prominent applications that have been investigated, but I'm not able to discuss that because that's classified information. But also recycling, we have done some recycling ourselves. We can depolymerize this polymer and depolymerize quantitatively to the limonene oxide and CO2. But in the course of our studies, there was a nice paper published by De Koning and Sablon, who actually also showed by making use of the same catalyst that you can do this depolymerization reaction. But that's important for future applications where you can basically recycle, in this case, the most, let's say, important and expensive monomer of your polymer and reutilize that for making, again, a new polymer. So there are other things you can do. You can take the limiting oxide and a co-monomer and do a formal tauropolymerization. In that way, you can make tauropolymers where the amount of functionality, or basically double bonds, is something that you can control. So you can have a low degree of functionality up to a very high degree of functionality. And in that way, at a later stage, you can use the amount of functionality to design particular properties. It's shown over here. So the N over M ratio is reflected over here. So we have control via a process. And in one of these cases, we followed kinetically the incorporation of both, or actually, yeah, both of these epoxide monomers. So we know more or less what kind of polymer we have and what kind of degree of functionalization we have in the beginning and at the end of the polymerization process. So on this slide, it's just to show you that by having such a functional polymer, you can functionalize using these dithiols. This is standard chemistry using radical precursors, and then you can do a radical addition to these double bonds and interconnect different polymer molecules, making them more rigid. And then you can study, for instance, the glass transition temperature and the decomposition temperature. And what we saw in one of these cases is an increase, a significant increase in thermal stability. So we have a very high glass transition temperature and a substantial increase in thermal decomposition, as you see over here. This is important because if you want to design polycarbonates that resemble to a certain extent commercial polycarbonate that has a very high glass transition temperature of around 150, then you can see that we're now getting very close to what is considered to be attractive in this respect. Then we also decided to look at, a little bit more into the functionalization of this double bond. And as you see over here, we can make that polymer. This is our parent molecule, our parent polymer. And by doing an oxidation reaction, we can actually introduce here an epoxide. And by doing so, what we see is that the TG is increased from about 110 to 131. But when we then do further chemistry on that epoxide, we make here a cyclic carbonate ring, we can actually extend that TG, that glass transition, to 178. And this is now, I think, one of the highest glass transition temperatures reported to date for a polycarbonate. Also, we see an increase in thermal decomposition and a processing window of about 50 degrees, which allows us to really think about utilizing these kind of polymers or pre-polymers in polymer applications. I'd like to highlight one thing. So this chemistry was communicated via our communication unit here at ICIQ at our institution. And in a blink of the eye, we saw that the chemistry was highlighted in many different forums. So one of these is the India Times. That surprised me to a little extent. I was very happy to see that. So the India Times, of course, has a readership that is quite substantial. But there were also other newspapers here in Spain that highlighted the work as a potential first step towards an alternative for for the commercial polycarbonate. Okay, I've come to the end of this presentation. So hopefully I've shown you today that non-reductive transformations of CO2 can create a whole new set of transformations where we can recycle the carbon that is typically emitted in many different, let's say, combustion processes, and in that way valorize these compounds into a wide range of fine chemicals, pharmaceuticals, and polymers. And also, the second thing that I want to highlight is that new conceptual approaches are indeed needed if you want to increase the complexity and substitution degree of these pharmaceuticals and polymers. And the link with the applications I've tried to make at the beginning of my presentation. So the functionality is extremely important in order to think about possible applications in synthetic chemistry, but also polymer chemistry. Last but not least, I thank the people whose names have appeared during this lecture, also former members, not all of them, but at least the most important ones that have been highlighted today. Those are shown over here. The collaborations with people that work in the field of polymers or in the design of new catalysts, also from Italy, as you can see over here, and people that have with whom we have collaborated in terms of mechanistic analysis by theoretical approaches, and also people at ICIQ that have helped in the development of the polymer chemistry. The funding agencies that are listed over here, but also the support from several companies, those are listed over here, and CO2 value, which is a general, let's say, organization that helps to promote the use of CO2 in, let's say, in commercial applications. The last slide, as you can see, is the most simple one. Here you see smiling faces. People are being very happy, at least this day. We also make fun in different ways. So we have a typical barbecue and casotala, which is very typical for the Catalan region. And with this, I'd like to conclude my presentation. I'm looking forward to any comments that you may have, and thank you very much.
Thank you, Arjan, for the very insightful and interesting presentation. Of course, I will ask all the audience, and considering also the delay on the stream presentation, I ask the audience if there is any question, just to write in the chat of YouTube, send a message anyway, and we will forward to Arjan, to Professor Kleij for his answers. Meanwhile, I want to ask Arjan, you have of course you have plenty, you have investigated several different areas in involving CO2 and the catalysis of CO2 mainly. Just recently, if I'm not wrong, you have also contributed to some heterogeneous catalytic approach for the fundamental process of preparing cyclic carbonate. What is your comment in general for the heterogeneous catalysis in the reaction in the general, not of course for the polymerization maybe, but in general for the reaction you have been investigating? What could be the best opportunity? What do you think?
Yeah, so I think this is a very important question, which I have to answer in two different ways, or are basically two aspects that are very important. One, of course, if you want to make this commercially viable, then obviously a heterogeneous catalyst has much more advantages. Second, heterogeneous catalysts typically are less flexible in the synthetic, let's say, modularity that you can have. So that has everything to do, of course, with the sterics that are involved in a number of these, let's say, transformations. So if you have a sterically bulky substrate, then obviously I think a homogeneous catalyst would work much better and would be preferred. However, if you talk about the relatively simple transformations, between CO2 and simple epoxides, then obviously a heterogeneous catalyst is the preferred choice. And as you said, and as you correctly pointed out, we have been working on that in collaboration with some colleagues here at ICIQ. So we can support catalysts, we can make even bifunctional catalysts on the support. In that way, we can recycle the support, we can have recyclable catalysts that works very well. But a recent result that we also have obtained is the immobilization. What we have carried out is an immobilization of a very simple molecule onto a heterogeneous support, and to use that in flow catalysis. So for instance, to make glycerol carbonate or glycerol carbonate, and that of course is one of the more important carbonates. So I think that shows very nicely that if the synthetic complexity is reduced, you can actually turn to heterogeneous catalysts and even think about flow catalysis, and in that way, hopefully have productive formation of important cyclic carbonates, because most of the carbonates that I've shown you today are relatively useless, to put it like that, from a commercial point of view. And in my view, there are three types of carbonates, or three carbonates that are commercially attractive: ethylene carbonate, propylene carbonate, and glycerol carbonate. So those are the ones that you would like to focus on. And what I already mentioned, by making use of the heterogeneous catalyst, you can do that chemistry. So yes, heterogeneous catalysts or catalysts are extremely important to consider in terms of commercial applications.
Thank you, Arjan. In fact, you mentioned the key aspects that I expect to hear. In fact, it's very interesting. And also you mentioned something very interesting about the most important carbonates, which are commercially relevant. And also at the beginning, you mentioned the fact that some of these carbonate, propylene, I think carbonate is used for batteries. To this, and in general also the carbonate you mentioned that they are also they feature very low toxicity as well, while these aspects have been somehow not very much investigated in terms of data related to toxicity of the advantage of having a carbonate instead of other functionalities, which is something very interesting.
I think you touch upon a very important point. I think there is reasonable data available for ethylene and propylene carbonate, but when we discuss slightly different carbonates, maybe even glycerol carbonate has not been investigated that much in terms of, if it has any toxicity issues. And so it's difficult to predict where this will lead to. I mean, carbonates, yes, cyclic carbonates have potential as electrolytes, and there are some sophisticated carbonates that have been developed where, for instance, boron atoms have been incorporated into the cyclic carbonate structure, producing basically a boronate, or a borate, maybe I should say, a type of salt, and those were investigated for their, let's say, applicability and their usefulness as an electrolyte. So there is some data available, but not very much, So I think one of the big applications so far of ethylene and propylene carbonate is as a non-protic polar solvent. That is, I think, one of the most important applications. I think for glycerol carbonate, this is a very interesting one. Because there are much more, let's say, applications for scene, and this is still, I think, a subfield that is being developed, and I expect to see much more movement in this area, and maybe mostly focusing on glycerol carbonate.
Thank you.
I have a
question from the audience.
I have a question, Luigi. Arjan, about the polymerization with CO2. So I think it's many years that many groups try to obtain polycarbonate with different epoxide. Most of the catalytic system work very well with the CHO or CHO-like substrates. But what do you think will be the development of polymers from CO2? There is a real room for the development, or just the commercial available polyurethanes is the maximum that we can obtain from CO2 polymers?
No, excellent question. I believe that there are a few aspects that are really important. One is availability of your raw materials. So we know that limonene is readily available, and in principle, the market has the potential to grow even further. That aside, I think also you need good catalysts. And if a catalyst can do cyclohexene oxide CO2 copolymerization, it doesn't necessarily mean that it can also address the copolymerization of limonene oxide and CO2, because it tends to be, let's say, a challenging reaction. And so far, as you probably also know, there are only very few catalysts that can actually make this polymerization to work. It's important also to note that for the relatively simple epoxides, for instance, propylene oxide and CO2, you can do, of course, copolymerization, but most catalysts, they fail to produce, let's say, very high molecular weight of polypropylene carbonate. And the reason for that is very simple, because the backbiting is much more favored, yeah, in most of the cases. So you can form an oligocarbonate, but the backbiting and the depolymerization is actually very much favored at relatively low temperature. So it's difficult to get high molecular weight and at the same time prevent that depolymerization. That has everything to do when you look at, transition states of catalysts. For instance, with cyclohexene oxide, there is a clear steric hindrance, so the propagation is preferred over the depolymerization, unless you go to very high reaction temperature. So I think if we really want to advance the field, we need to focus on cheap starting materials, available materials, and if we, for instance, think about terpenes, that is a possibility, but not necessarily the only possibility. Then you need improved catalysts, because if they resemble, at least to some extent, the reactivity of terminal, maybe di-substituted epoxides, so non-cyclic epoxides, then you have a problem. There are very few catalysts that can actually make that reaction happening. So yeah, what is to be expected? I think there will still be a lot of room for other alternatives. So one alternative is, for instance, making a 6-membered cyclic carbonate and do ring opening polymerization. Because I think a 6-membered cyclic carbonate you can make in different ways. I've shown today 2 new ways of doing so, but there is still a lack of synthetic procedures, simple ones, that allow you to have, let's say, a reasonable scope of these structures and to investigate the influence of their substitution and their functionality on the eventual polymer properties. So there is a lot to gain over there. But then again, as I said, we need to develop new methods for these carbonates. And then once you have the 6-membered cyclic carbonate, you can do ring opening polymerization. And typically, you would retain the CO2, because Darren's work has already shown that in principle, the formation of the polycarbonate is preferred over the decarboxylation of the 6-membered cyclic carbonate, at least in the cases that he studied. So there is, I think, a potential out there. But there are 2 ways you can go, either addressing new monomers or existing monomers, but with improved catalysts. And on the other hand, you have a different way of polymerizing. So instead of the copolymerization, you use ring opening polymerization, but then you would have to design other types of CO2 building blocks. That is a little bit my vision.
Thank you.
Yeah. Luigi, I have one question. Luigi.
Sorry, please, you may proceed with your question, please.
Okay. Arjan, beautiful chemistry, beautiful lecture. So I have thoroughly enjoyed. So my question, I have also seen recently you have started photocatalytic transformation. I'm pretty sure you have also tried in your lab for similar or a bit different chemistry. So I would like to hear some of your experience. Have you seen or have you observed any complementary reactivity for the formation of carbonates using photocatalysis?
Well, yes, so that's a very sharp remark and a very good idea. We are developing as we speak projects in which we want to use photocatalysis, photochemistry. So one example I showed, which we are about to finish, hopefully very soon, where we make use not necessarily of a CO2-based building block, but you can envision that it should be possible to take an allylic alcohol, react that with CO2. Of course, that equilibrium is disfavored, but by favoring that equilibrium towards the next stage, let's say a protected version of that allylic alcohol, we should be able to get into chemistry, radical chemistry, for instance, that is photo-mediated, and in that way fix the CO2 into a larger ring carbonate. One of the ideas that we have is to use also similar photocatalytic techniques for making even larger rings, because that is still a very, very big problem nowadays, because you go against thermodynamics typically. And that is something that we want to address. So to come up with clever photocatalytic, not necessarily only photocatalytic, but photocatalytic as well, transformations that will allow us to if you like, to form a benzylic radical, but to have a space that is sufficiently large that will then eventually allow you to make a 7-membered or 8-membered or even an N-membered cyclic carbonate. And then, of course, to understand their reactivity towards the formation of polymers. Yeah.
Thank you, Arjan.
Thank you.
Arjan, we have a question from University of Milano, Emma Gallo, who congratulates you for the presentation, and she would like to know if you test aziridine instead of epoxides for the 6-membrane ring.
No, we haven't done that. That's the short answer, but yes, it should be feasible. Yeah. So there are other examples in the literature, not reported by ourselves. So Michael North, for instance, he used aziridines and also aziridines with alcohol functionalities. And I told him once that I think in his reaction, he's actually doing the chemistry that we have been proposing for several years. So by making use of an Lewis acid, you can activate the alcohol, bring open the aziridine, but then you can equilibrate to the cyclic carbonate as a second step. So he was focusing on cyclic carbonate synthesis, but I think there are 2 mechanisms in order to get there. So the answer is yes, you can use aziridines, but there is one but. Aziridines are typically less reactive. And typically you have to use protected or N-protected aziridines. Those tend to react a little bit better. Not in all cases, but in most of the cases. So there is certainly potential for CO2 and aziridine reactions to work, and also to make 6-membered cyclic carbonates or oxazinones, as they are called, oxazinones. So yes, I'm certainly that it's possible, but we haven't focused on that. Thank you.
Thank you, Arjan. And I believe if there's no other question from the audience, I thank you again for the nice presentation, and we may proceed for the presentation of Shoubhik. I will leave the chair to Carmine. Thank you again, Arjan, and Carmine, please.
So thank you, Luigi. It's my pleasure today also to introduce Professor Shoubhik Das, who is not only a colleague but also a friend. He did actually almost all his academic career in Europe. He did his PhD in the group of Professor Matthias Beller in Germany, in the Rostock, in the Center for Catalysis, and then he received his PhD in 2012. Then he joined the University of Cambridge, working as postdoc in the group of Professor Matthew Gaunt. And after that, he moved to the ETH in Zurich, working in the group of again as postdoc in the group of Professor Paul Dyson. Then he moved to Göttingen again, back to Germany. And where he was a junior professor at University of Göttingen, and from the end of 2019 he moved to Belgium, to Antwerp, where he is now professor of organic chemistry. His main research interest is the activation of small molecules like CO2 and their application in organic synthesis and fuel generation. In the last years, he also moved to photocatalytic reaction. I think it's right, Shoubhik. So the title of his presentation is Do we really need transition metal for CO2 promoted reaction and others? So we will try to respond to this question. Please, Shoubhik, the floor is yours.
Carmine, thank you very much for the kind introduction. Thank you for the invitation. I also thanks Luigi for hosting all of us and all the Italian colleagues, those who are presenting. Thank you, Arjan, as well, for the beautiful chemistry. Arjan, will you mind to switch off your screen? Then probably I can share.
You can. Shoubhik.
Can I?
You already done.
Oh yeah, now it should work. Yeah, I hope all of you can see my screen now. Can you all see my screen?
Yeah, it's okay.
Okay, super. Yeah, so the question is, do we really need transition metal for CO2 promoted chemistry? So this is what I would like to convince or like to explain you in the next 40 minutes. In my group, so already Carmen has given the brief introduction. So we are doing photocatalytic transformation, although we started with CO2-based chemistry in 2015 in Göttingen, and then slowly we moved to photocatalytic transformation. I will also try to explain like why we switch to photocatalytic transformation. We had particular reason to switch over to that chemistry. So please bear me for the next 40 minutes to explain me all these things. Obviously, CO2 is our main interest at this moment to transfer parallel to CO2 chemistry. We are also working with oxygen-based chemistry. However, to go into more detail into that area, I would just like to give some general perspective. So what is the real problem at this moment? I guess all of you will agree with me that the COVID situation is kind of very chaotic. Think about that if this program was organized, let's say 1.5 years before, then probably me and Arjan would have been in Italy and then would have been sitting next to Luigi and Carmen discussing all the scientific, non-scientific things. And after the lectures, we would have been to nice Italian restaurants, enjoying the nice foods, beer, and blah, blah, blah. Yeah, that was ideal. But situation is no more in the similar way. So we became kind of used to with the normal situation, or I would say abnormal things. Like we have learned many things. For say, we have learned some social distancing, how to maintain these things. We have also learned like how to survive with a long hair. So once upon a time, especially in our teenager period, so we used to think like, okay, having a long hair can give you some new look and things. Yes, obviously, but later onwards we realized that, well, it's fine to have a bit smaller. But nowadays, actually, we became quite used to with this situation. Not only that, we have also learned some tricky ideas how to maintain social distancing. The particular problem is with the education for the younger generation. Even in the university here in Antwerp in Belgium, we are also kind of getting a lot of complaints from the students that they cannot concentrate. Yeah, there are several reasons for that, but to be honest, that's kind of a particular area, and I'm pretty sure that all the teachers or professors, those who are listening my lecture, they will agree that we all actually would like to talk with you guys, with all the students personally, or probably face to face. That makes us, or that gives us a very good feeling to provide what we are going to teach you. At the same time, we have also learned the word quarantine. So this word has become very popular. We have learned many tricky things, creative art, creative thinking, and all the many things. And that also gives us several things. Yeah. The consequences during this lockdown period, we have learned many new things. And we are also kind of we became quite bored actually, because we had to do the similar things. We are not allowed to go outside, or we cannot do any out sports or any visiting any other places. But meanwhile, we had some people who are kind of entertaining us. So our neighbors, our friends, our main people, I don't think I need to explain them actually in the pictures. So they also tried to kind of entertain us in a various way. However, all of them are kind of, in the natural way, I would say, or in the national period. I left this place kind of empty. So I asked my Italian colleagues, you can pick up the picture and you can put it, and you can, I'm pretty sure that you have some different aspect or different dream, how you have been entertained by your own people. But among all the peoples, I think a very international person, or who has actually entertained us very internationally, he has nailed it. I mean, to be honest, I mean, think about, we are all sitting in the lockdown period, watching TVs, movies, and these things. but we need something exceptional, and he did it. I enjoyed it, and I kind of salute him. Thank you. But apart from that, while we are discussing all these things, what we kind of overlooked is that, meanwhile, the CO2 level or the different other greenhouse gases level kind of decreased, which is good, fantastic. But does that mean that we should stay under the lockdown period for a longer period? No, we cannot. So that means as soon as the COVID situation will improve, or the situation of our life will become normal, situation will become drastic, yeah, the CO2 level and things will become completely dramatic. And this is what all the environmental chemists or the people who are directly involved with it, they are pretty much annoyed, because there will be several other consequential effects, like economic recession. It's already started. There will be biodiversity problem, many other things. However, for the time being, we can be kind of happy to see these kind of pictures. Let's say for the Venice, you know, me and my wife, actually, we love Italy very much. Yeah, so we have been 3 times there. My wife's personal overview is that Venice is very romantic. Yes, I agree. But economically, I need to think twice. However, meanwhile, if you look at the picture, the water level in 2019, and if you compare it to 2020, it has become pretty cool. I think all of you know that this is nothing new. From the satellite picture, the picture from 2020, it looks, the water color looks much more deeper, because all the sediment now went down because of less traffic or less boats. They are traveling throughout the water. And this is the particular things that we need to address, that this situation is only temporary, only for the COVID period. Situation will completely change in 1 year, as soon as the things will become normal. And then we have to address these things. So we have to now actually behave much more carefully, that how we can address this problem. Let me show you one of the examples. All of us, we need to wear masks. So there is no exception. There is no exceptional situation. However, do we really need to wear a very matching mask? It's not. Well, you look handsome, you look beautiful, this is fine. But what we are forgetting, that we are generating a lot of these things. So we have to be careful as well. And as soon as this situation, this COVID period completely get over, situation will become even more dangerous. We will again come back to the previous stage. And therefore, we have to behave very carefully. We have to do things very carefully. And we have to think about much, I would say, sensitive way to act, to react as well. And this is where I think chemists, we need to think very carefully. Because particularly chemists, actually, we are producing a lot of chemical waste. We should be very thankful to Roger Sheldon for his metric system, this E factor. And you know, higher the E factor, that means that the amount of waste we are generating quite higher. And particularly if you compare different industrial sector, the pharmaceutical and fine chemical sector are quite high. E factor is around 25 to 100 region. So therefore, we need to definitely address this area, that how we can change this generation or the amount of chemical waste in our system. Of course, we need to design our reaction in that way. We can think about several tricky things, but we can also avoid in another way. And therefore, to address these things, some green chemistry principles are also, I would say, organized or well known. So I'm pretty sure that all of you know these things. Particularly, we need to use the green solvents. We need to use the green catalysts, some efficient processes we have to think over. We have to also consider environmentally benign products. But moreover, what is important is the green and renewable raw materials, utilization of them. And when I talk about green and renewable raw materials, of course, carbon dioxide, oxygen, biomass, they are kind of a key areas in today's research. And this is why we need to consider, or we need to put our focus on CO2 and oxygen-based molecule, or utilizing biomass molecule. You have already learned from Arjan's like how to utilize carbon dioxide in organic synthesis. So he tried to fix the CO2 molecules in the organic molecules to achieve new molecules. However, I would actually like to show you the different other perspective of the other area of CO2-based chemistry. But before going into there, I would like to show you like what has been done with CO2. So one of the, I would say, organic synthetic aspect, you have already got the essence from Arjan. However, not only organic molecules, CO2 has been transferred into methanol towards formic acid, methane, carboxylic acid, different alcohols, and these part polycarbonates and carbonates Arjan has already covered. In fact, now it is asymmetric synthesis are becoming also popular with carbon dioxide. I am thankful to all of them, particularly Arjan is here, Carbin is doing fantastic iron-based chemistry, our Italian colleague, Michele Aresta, Gabriele Senti, I mean, they are kind of a pillar in CO2-based chemistry. So I'm thankful to all of the people who are kind of working in this area and putting pioneering efforts in this chemistry. So this is all about CO2 fixation into organic molecules. But I told you that compared to CO2 fixation, I would like to show you more towards a CO2 promoted. CO2 will be kind of a promoter in your system. What does it mean? So CO2 promoted reaction means, so you will start from functional group 1, you'll put carbon dioxide, you will do your reactions, and then you will completely get a new functional group. And meanwhile, your CO2 molecule is not incorporated in your molecule. I will explain you in a bit better way within a very in a short minute. What is the consequence of this chemistry? Obviously, if you utilize carbon dioxide, because it's a non-toxic reagent, so it can avoid some toxic chemicals like oxalyl chloride or phosgene and this type of molecule, even carbon monoxide. You can also provide some alternative reactivity and selectivity pattern in your reactions. Not only that, you can also generate some novel reactivity concept from CO2-based chemistry. So that's the beauty of the CO2 promoted reactions. What is this principle? So here is your functional group 1. Now you have incorporated carbon dioxide in your system, so you have formed the CO2 adduct. Now you do the catalysis, so you do your desired transformation, and very finally, you take out your CO2 molecule and you get the new functional group. So CO2 will do its job, and then at the end of the reaction, you take out from your reactions to achieve a new molecule. This is the overall layout principle of this chemistry. Some of the examples, if I give you, probably it will become more clear. So Imad actually, he has published in one work in 2007. So he has found that if you have this hydroxy group next to your alkyne moiety, if you use CO2, this CO2 will directly combine with the hydroxy group and you will form this O-carboxylate anion. This one then further rearrange into your molecule. And at the end, if you release carbon dioxide, you get the rearranged product. So this chemistry is not possible without using CO2 in his system. Second example from Benjamin List. So he used this allylation reaction, or I would say enantioselective allylation reaction. He wanted to do allylation reaction on the alpha carbon of a carbonyl compound. What he has found, when he has done CO2 or in the presence of carbon dioxide, the enantioselectivity is quite higher. Not only that, several other chemists like Tom Robbins and Franziska Schonenbeck, they have developed this chemistry. So they are trying to synthesize lactam moiety from amino compounds via Michael addition reaction. So they have used carbon dioxide in their system. They protected this amino group from these carbamate type structures. Then they use photocatalytic transformation, HAT type transformation. They generated one carbon-centered radical, and this radical then underwent this Michael type addition reaction, and finally CO2 was released from the system to generate this lactam moiety. A very final example from Lee group from Denmark, actually, he has shown that cyanation reaction on the benzylic CH bonds can be possible in the presence of carbon dioxide. The role of CO2 was kind of to combine or to make an adduct with this oxygen atom so that this hydrogen, this CH bond can become much more weaker, and then followed by the cyanide anion can attack on that position to achieve this product in a much facile way. So that was the overall principle. However, one thing I must admit there, this chemistry was actually developed by Shell in around 1970s. And they were kind of trying to find one additive for their oil industry. Unfortunately, they have found that in the presence of carbon dioxide, the separation of the desired product was fantastic, selectivity was excellent, but they could not have been able to provide the actual explanation in their chemistry. Later, people have tried to solve this problem, and now the picture is much more clear, like how this CO2 promoted chemistry is going in for the synthesis of fine chemicals or pharmaceuticals. Not only this chemistry, so you can also do various other type of reactions like arylation reactions. So Laros actually has done several of this arylation chemistry using the CO2 promoted chemistry. You can also do olefination reaction. Alkylation, I have already explained you. Diketone chemistry, I'll show you. Oxidation chemistry, I'll show you. You can do reduction reactions. Cyanation, I have already explained you. And also dehydrogenation reaction, you can also achieve in the presence of CO2 as a kind of a promoter. And this type of reactions, I will explain you today. So not only for this kind of chemistry, but this chemistry has been also applied for the synthesis of different pharmaceuticals like quinine, secretase inhibitor that also you can synthesize using this principle, some anti-malarial agent, harmine and anacetrabib, corrosive inhibitor, dihydronifedipine, combretastatin, A4, many of these pharmaceutical drugs and other utilizable molecules you can also synthesize utilizing this chemistry. Some of the drugs I will also show you today. So we have started this chemistry, I would say, in around 2015, end of 2015. And then we are trying to find a niche in that area, like in which direction we can take that chemistry. What we found is interesting that so far, actually metal-free, or I would say in a better way, transition metal-free catalytic system are not so popular for this chemistry. So we thought probably we can utilize this concept and can also try it for different oxidation reactions. In fact, I guess all of you will agree that metal-free catalysis or transition metal-free catalysis are also becoming popular because of several reasons, like it can also provide sustainable catalysis. It does show some high catalytic reactivity. It's kind of environment friendly. Of course, there are several exceptions here, like transition metal-based chemistry as well. You can also utilize for asymmetric synthesis. Many of the cases, they are very cost effective. Some of the example I'll show you. And in fact, you can also utilize for large-scale synthesis. So it does have several advantages, and these are the advantages we wanted to take it forward for the synthesis of valuable chemicals, fine chemicals, pharmaceuticals, and others. With these things in our mind, we started to think about how we can do this chemistry, particularly oxidation reactions. So you will probably call me a mad if I try to convince you that oxidation chemistry is we need it. We need to find a fantastic catalyst. Indeed, there are plenty of catalysts. Yeah, there are 1,000 transition metal-based catalysts. Then what is new? The problem is, in Pfizer, in pharmaceutical industry, you can read this paper. This is a fantastic paper from David Perry. He's from Pfizer. So he actually mentioned in Pfizer, still they are using metal-free system for the oxidation reaction. And you know, pharmaceutical industry, metal-free systems are quite popular. So in Pfizer, these are the 4 methods that they are using for the oxidation reaction, particularly oxidation of alcohols. Soil oxidation, all of you know, it's super popular. Fitzer-Moffat, a bit less popular, but still people use a lot. Parik-Doering oxidation, Albright-Goldman oxidation. If you look at all of this oxidation reaction, what you need? You need some promoter like oxalyl chloride 3 equivalent, DCC 3 equivalent, pyridine sulfonate 3 equivalent, acetic anhydride 20 equivalent. Not only that, you need super stoichiometric amount of the base. For say triethylamine, 5 to 6 equivalent. Isopropylamine, roughly 6 equivalent. Many other cases. So obviously the amount of waste will be quite higher, and this is what we need to address. And this is why we thought, can we replace this promoter like oxalyl chloride, DCC, or pyridine sulfonate by carbon dioxide? And this chemistry will be even more interesting if we can provide a catalytic strategy. So that means our base, rather than stoichiometric, can we utilize it in a catalytic way? That was the main strategy. How we can do that? So before going to do our reactions, we are trying to think about the actual reaction mechanism in that system. If we take our look in soil oxidation reaction, how does that reaction go? you have this oxalyl chlorine, you have this dimethyl sulfoxide, they combine together, you release carbon monoxide and carbon dioxide, and at the same time, you generate this active species. And this active species later combine with the hydroxy group, so your hydroxy group becomes a good leaving group, and you end up to here. And now actually, I don't need to explain you, if you have the base, you can directly convert you to the carbonyl compounds, because it's a very good leaving group, and this H plus is much more facile to take out. So the key point here is that to reach to that stage. So if you can reach to that stage, then actually your oxidation reactions would be much more facile. And this is what actually we wanted to do. We wanted to reach at this stage. How we can do that? So our planning was, if we start with the hydroxy group, we can activate with carbon dioxide, so we can form this O-carboxylic acid. DMSO has a slightly nucleophilic character. It's not super nucleophilic, but it does have some nucleophilic character. There are several articles on that. And this nucleophilic character we can show in our chemistry. So if we bring the nucleophile here, if it can attack in this carbon center, then we can release this bicarbonate. I'll come back in a minute in this stage. And at the end, we can end up to this intermediate, which is exactly similar like in the Swan oxidation. And that means if we add the base, we should be able to reach towards the oxidized product. However, in our system, we have one advantage. So we are generating bicarbonate. And if we are generating bicarbonate, this conjugate acid of the base can be made free. And now you can utilize base actually in a catalytic amount. That was the overall concept for this chemistry. And this is how we wanted to achieve catalytic way to synthesize CO2 promoted oxidation reaction to provide an alternate reactivity in metal-free oxidation chemistry. Now actually with these things in our mind, we went to the lab, we started screening different bases, and what we did found, like if we have K3PO4 20 mole %, if you can heat at 90 degrees centigrade, you can directly make this selective oxidation of hydroxy compound. This reactions is not only for the primary, it can also work for the secondary alcohol. Some of the examples, so we had several, some of the important example I wanted to show you. This thiomethyl group is one of the examples. So if you want to oxidize, or if you want to do the oxidation reaction in the presence of oxygen using transition metal chemistry, you cannot stop oxidation of the sulfur atom. It's impossible. However, with the CO2 chemistry, you can do this oxidation very selectively, and your thiomethyl group will be completely intact in the reactions. Another example is the aldehyde moiety. Again, the same principle. If you have the aldehyde, you cannot stop the further oxidation. And this is what is actually quite well known. If you have benzyl alcohol in your lab, if you keep it for, let's say, 1 year, you will see that the end of the bottle, you will see some solid materials, which are kind of the acid, actually, the benzoic acid, because it gets oxidized in the presence of the air. However, in our system, we didn't see any oxidized product from the aldehyde. So overall, this chemistry was completely intact in the presence of different oxidizable functional groups. Additionally, we can do several, I would say, allylic conjugate or conjugated alcohol compounds and some other secondary alcohol as well. However, this chemistry was limited bit of for this aromatic and conjugated alcohol compounds. Nevertheless, we are thinking like how to apply this concept for other synthetic application. So one of the example that we actually rationalized, synthesis of this conjugated carbonyl compounds is quite important for sanobenone B, 11-cis-retinol, and there are many more compounds which have this kind of conjugated carbonyl functional group. Can we provide a direct strategy to synthesize them? To do that, we started from the cinnamaldehyde compounds, and we added this vinyl magnesium bromide. So obviously, if you are adding some Grignard reagent in your cinnamaldehyde, you will generate one secondary alcohol. Now in the presence of water and 1,4-dioxane at 100 degrees centigrade, we can further transfer via rearrangement your secondary alcohol to the primary alcohol. And finally, we can do the oxidation reaction using our strategy, and you end up to this conjugated, homologated carbonyl compounds. So this whole procedure is in one pot, but 3 consequential steps. Not only that, you can also try to synthesize some of the pharmaceutical molecule like combritastatin A4, DMU 212. The principle is pretty much similar. So you start from this hydroxy compound, you oxidize it using this metal-free strategy, you end up to this aldehyde, and then you do Wittig type reaction to end up to this kind of pharmaceutical molecule. So these molecules are quite small. I mean, it's not at all challenging. However, this is the first strategy that can provide you a metal-free way to synthesize this kind of pharmaceutical molecule. After doing all these things, we are thinking, what is the mechanism? Of course, we have had something in our mind, but until I'm giving you some proof, I'm pretty sure you will not be convinced. And if you are not convinced, then of course you will not be motivated to do this kind of chemistry. So I already explained you that if you have this hydroxy compound, at first we wanted to activate this hydroxy compound in the presence of carbon dioxide so that we can form this O-carboxylic acid. We tried several strategies to trap this molecule. However, we are every case is unsuccessful. It's quite clear because this molecule is very unstable. However, what we realized, if we transfer this carboxylic acid to the corresponding carbonate, you learned a few minutes ago, this carbonate chemistry from Arjan. So this kind of carbonate could be stable compared to this molecule. And this is why we used alkyl iodide in the system. We have also used 13 CO2 level instead of carbon dioxide so that we can directly detect this molecule. In fact, via HRMS, we can directly detect this molecule. Additionally, we have also replaced DMSO by DMSO 18 to see what is the role of dimethyl sulfoxide in that chemistry. And what we have observed that O18 actually is incorporated in the final product. And we have seen 99% labeling in the final product. To further prove it, whether DMSO is the real oxidant in our system or is carbon dioxide is the oxidant. So obviously we have checked all the other reduced product from carbon dioxide via NMR, via headspace GC. We have not seen any reduced product from carbon dioxide for say formic acid, formate, or carbon monoxide. Nothing we have observed. So what's happening? What is the oxidant? Of course, if one of them is the oxidant, then we need to find out what is the reduced product in the reaction. And this is why we actually replaced this dimethyl sulfoxide with butyl sulfoxide. And now actually we have observed that dibutyl sulfide we are generating and the ratio of the product of this carbonyl compounds and the dibutyl sulfide is exactly in the same ratio. Just try to memorize your chemistry that in the redox neutrality principle, if one of the molecule is oxidized, the other one has to be reduced in the same ratio. And exactly this is the principle. So our alcohol is getting oxidized and dibutyl sulfoxide or dimethyl sulfoxide, they are getting reduced in the system. So that means DMSO is the real oxidant in the system and there is no transformation occurred for CO2 molecules. So CO2 kind of act as a promoter in the whole system to completely transfer one functional group to the another. So while we have done all this chemistry, we are also thinking particularly to go towards the other aspect of the CO2 promoted chemistry. So one of the idea which came to our mind is that can we apply this chemistry for CC bond formation reaction, carbon-carbon bond formation. And when I talk about carbon-carbon bond formation reaction, all of you probably will agree that benzoin type reaction is very popular in the presence of NHC carbon. What we realized, compared to this alpha hydroxy ketone, these diketones actually much more popular. In fact, what we can do, so we can start this cross benzoin reaction in the presence of this NHC carbon or thiazolium carbon particularly to say, and then followed by that, we can do oxidation reaction using CO2 as a promoter so that we can get this building block, which is very popular in pharmaceutical sector or chemical biology sector. And now actually in the presence of this thiazolium carbon, we can directly combine two different aldehyde. We can form a new carbon-carbon bond here so that it can give you a ready access or easier access to synthesize diketo compounds. You can synthesize both symmetric and non-symmetric diketone. Particular attention is that this chemistry doesn't work in the presence of nitrogen. It's obviously because it don't promote the oxidation reaction. The chemistry also doesn't work in the presence of oxygen, because in the presence of oxygen, your thiazolium carbene won't be stable. And we have checked that this chemistry only works in the presence of CO2 atmosphere. Without CO2, you won't see any product in that chemistry. So with these things, actually, we have done some substrate scope, which is very natural for the catalysis people. And now we can see several syntheses of several symmetric diketones starting directly from the aldehyde compounds. However, is that interesting? This is not so interesting, because there are plenty of methodology for the synthesis of symmetric diketones. However, one of the examples I would like to show you or share with all of you, this para-dichlorodiketones in sigma Aldrich, it costs 10 milligram, 119 euro. In other companies, it costs roughly in between 300 to 500 euro for 5 gram. So it's very clear that this compound is quite expensive. Now, actually, with our strategy from the parachlorobenzaldehyde, which is a very cheap reagent, we can synthesize directly this molecule and can apply it for the synthesis of neuroprotective agent, anti-malarial agent, and many other follow-up things. However, still I would suggest, or I will tell you, that the synthesis of symmetric diketones are not really that interesting. The most challenging part is that how we can go towards the non-symmetric diketones. Think about what is the traditional synthetic pathway. The traditional synthetic pathway for the non-symmetric diketones is that you need to use oxygen atmosphere, and then you have to do the oxidation reaction of the alkene and alkyne, and then only you can get this product. However, you need to keep in mind that not all of the non-symmetric alkene and alkynes are commercially available. So you have to synthesize them prior to your oxidation reactions. However, if we can provide this strategy directly from aldehyde, it becomes much more simpler, as all the aldehydes or carbonyl compounds are commercially available mostly, and they are quite cheaper as well. Obviously, there are some exceptions, but most of them are quite cheaper. So therefore, we thought we can provide a direct strategy for the synthesis of non-symmetric diketones starting directly from the aldehydes. And now you can see you can synthesize several of these aromatic, heteroaromatic diketones in your system. One example is particularly very favorite to me is this one. So it's one molecule where you have been able to pick up one electron withdrawing group, electron donating group, and one electron withdrawing group in your system. And by this way, you can make several combinations in your system. So now actually I have already explained to you like how you can utilize CO2 promoted chemistry for the oxidation of hydroxy compounds or hydroxy group. What happens if we would like to extend this principle for the dehydrogenation reaction? So this is what actually it came to our mind. And then we started screening several of these reaction conditions that we had for our alcohol compounds. That different base, different CO2, different temperatures, different solvent, at different ratios. So we have played all these things. The net result, the net conclusion was the major product was carbamate in all the system. We have observed this dehydrogenated product, but it was not so high. It was quite low in amount. However, when we have seen that the formation of carbamate we can get at atmospheric pressure at room temperature, we also became quite interested. It looks quite nice because many of the carbamate structures are quite popular pharmaceutical structures. So if we can provide a very mild reaction condition for the synthesis of these carbamate structures, this is not bad. So we thought probably these basic conditions we can utilize for the synthesis of carbamates. And now under the reaction condition, we can actually transfer this nortriptyline or cinacalcet to more carbamate structures, and kind of it can be also applied for the late stage carbamation reaction of different amine moieties. One of the examples I would like to share with all of you, this Urb602 molecule. So this molecule is very simple. Synthesis, if I ask one bachelor student, so he or she will come to me and will tell, well, it's very simple. You bring this amine, you bring this chloroformate, you add a base, and then particularly pyridine or triethylamine, and you stir it for 1 hour, you'll get a quantitative product. Yes, it's true. However, while doing this reaction, what we are not thinking is that this chloroformate is actually coming from phosgene. And that we need to avoid. can we provide a strategy directly utilizing carbon dioxide for the synthesis of this molecule? Not only that, think about this Urb602 molecule. If you want to synthesize a big library of this molecule, the main point comes because this molecule is also quite popular in chemical biology ground or medicinal chemistry ground, and many of the professors or chemical biologists, they are still working to modify their reactivity in their system. So that means they need a big library, and not all the time you cannot synthesize your chloroformate from phosgene because not all of them are commercially available. So you have to synthesize in the lab. So this is why we thought maybe we can provide a direct strategy for the synthesis of this type of very simple molecule. And now actually our strategy is very simple. You bring the amine, you put carbon dioxide, you add the base, and you add some alkyl halide in your system, and you can get directly of these different derivatives of the carbamate structures, different analogs. And particularly if you want to make a big library, you can make it, let's say, in 1 month of this system. Similarly, if you look into the peptide chemistry, I'm pretty sure all of you know in peptide chemistry, these protecting reagents, they play a big role actually. And when I talk about this protecting reagent, CBZ, BOC, FMOG, they're actually quite popular. However, if you take a deep look into that, all of them are actually carbamate, all of them carbamate, the FMOG, BOC, and CBZ. So therefore, the principle is again similar. Because all these CBZ things, you use benzyl chloroformate. All the cases you use chloroformate. Can we replace all of these things with carbon dioxide? And now you see, for your phenylalanine, for your tryptophan, methionine, glycine, you can directly transfer to the corresponding CBZ protected amino acid utilizing carbon dioxide in your system. And this chemistry is not only limited to amino acid, rather you can also go towards peptide molecules, and this is quite tolerable under that reaction condition. We also didn't see any racemized product of the peptide carbon center in our reactions. This is good, this is fine. However, we still could not be able to achieve the CO2 catalyzed dehydrogenation reactions. How we can do that? We started thinking, and that's how actually we started to jump into the photocatalytic reactions. And you know, I mean, when nothing works out, you try to think about why don't you try some radical? Why I don't behave like a radical? Because radical part has a radical character, and that's the beauty. However, you need to provide this radical in a controlled way, and they are actually photocatalysis is, I think, one of the ideal. There are several colleagues, they are working. Of course, we cannot think the contribution from our Italian pioneer Giacomo Cimoscian. He has published in 1912 actually the science paper, and later actually 100 years later, or I would say, let's say 90 years later, this chemistry became much more popular. However, he's the main person, he's the main pioneer to develop this chemistry. What is the principle of the photocatalytic transformation? So you have this photocatalyst, you excited, this is your excited state, and this excited state can be oxidizing or reducing in nature. That's the beauty, that's the good part. And now, depending on your reaction, depending on your photocatalyst, you can actually play in other way. Either you can generate a radical anion or you can generate a radical cation in your system. And then when you have generated a radical anion, you also need to choose one other reagent so that you can close the loop and you can come back to the normal photocatalytic state. Same way here. So therefore, you can generate basically 2 radicals in the system. And now, depending on your creativity, you can combine in your reaction and you can follow up this whole strategy. And this is what actually we are trying to think, like how can we utilize this system in our dehydrogenation reaction? How can we go there? What could be our strategy? Our strategy was pretty simple. So this is our photocatalyst. We wanted to excite it. This is our excited state. And the excited state should combine with the amine, which is substrates, should generate a radical cation. This radical cation then, in the presence of the base and diameso, can form this oxo species, which is here. When we have this oxo species, we wanted to adopt one CO2 radical anion so that we can reach to this O-carboxylic acid. Just try to recall the chemistry, what I have shown you for CO2 catalyzed oxidation reactions. We also form these type of species in the system. Can we come to that stage? What is the challenge? If we can come here, then the dehydrogenation is not at all a problem. It should go fairly nicer way. The main challenge here is this part, the generation of this radical from carbon dioxide, because it requires roughly minus 2.21 volt. That's the problem. Of course, minus 2.21 volt, we should be able to provide, yeah? So if we want to do some fancy iridium catalyst with some fancier ligands, yes, it's possible. However, I already proposed to you that I would like to transfer this chemistry using a metal-free way or transition metal-free system. What could be the other strategy? The only strategy is utilizing UV light. However, if we try to kind of consider the harvesting solar energy and things, UV light is not really ideal because UV light only contains 5% of light in this whole solar spectrum. 40 to 50% is the visible light and rest is infrared light. So therefore, if we want to provide a sustainable strategy directly harvesting solar energy, we have to consider either the visible light or the infrared radiation. So that means this energy cannot be possible in the presence of different metal-free catalysts, metal-free photo or organic dyes. What could be the alternative strategy? So we thought probably rather than this CO2 radical anion, we can think about hydroxycarbonyl radical. Bokersley actually around 2010, he has proposed that hydroxycarbonyl radical can be generated via utilization of pyridine molecule. How does it go? So this is your pyridine. It reacts with carbon dioxide in the presence of the proton. You generate this pyridine carboxylic acid, and then this part actually undergoes some single electron transfer so that it generates this radical, and at the end, this molecule releases this hydroxycarbonyl radical. However, there are several, I would say, controversies about the generation of this hydroxycarbonyl. If you want to read detail about this, I would particularly request to read this paper. The main reason for that is that pyridine is a very stable heteroaromatic nuclei. So that means adoption of further electron here, it becomes much more challenging. And therefore, this chemistry, the main issue is the reproducibility. How we can utilize this chemistry in a high reproducible way. That's a very poor in this system. What we realized, probably instead of the pyridine, we have some household molecule like amidine type structures. So if you utilize this amidine for say DBU, DBN, these type of molecules are very well known in CO2 chemistry that it can activate carbon dioxide very easier way. So you can activate, you can reach to here. Then the follow-up principle is similar. The molecule should undergo single electron transfer. You generate this radical, and this radical can release hydroxycarbonyl radical. And if you look at the reduction potential value now, it's now minus 1.7 volt, roughly 1 volt less compared to the CO2 radical anion. And this value is in the range of different metal-free organic dyes. So once we have designed this strategy, we wanted to apply onto different dehydrogenation chemistry. Now we have seen that several organic molecules we can dehydrogenate under our reaction condition. However, it's very important that eosin Y is there, DBN is there, and CO2 is definitely has to be there. With this strategy, you can also synthesize different pharmaceutical drugs, let's say harmine, dihydronifedipine in your reactions. Not only that, several indolene type structures you can also dehydrogenate to undergo or to achieve indole type compounds. Several of these indole moiety you can synthesize using this strategy. So obviously the key things for this chemistry, what is the ongoing mechanism is lying behind it. So we have done all this control experiment in the presence of oxygen balloon, nitrogen atmosphere, no light, no catalyst, no base, there was no reaction. I told you already that it's very much necessary. We have also checked in the presence of BHT, which is well known for the radical quencher, and obviously it's a radical pathway so that the reaction was completely quenched. Surprisingly, when we added benzoquinone, which is kind of known as a trapping agent for hydroxycarbonyl radical, we have also seen the yield of the reaction was also dropped to 2%. So that means we have generated hydroxycarbonyl radical in our system. I'll come back to this point later. We also wanted to show that DMSO is kind of an oxidant very similar to our oxidation of alcohol reactions. So here again, we checked in the presence of dibutyl sulfoxide, and what we have observed that the oxidized product and the reduced products from dibutyl sulfide, they are in the same ratio. So that means, again, following the redox neutrality principle, that the dimethyl sulfoxide is the real oxidant in our system. And again, we also have not observed any reduced product from carbon dioxide, like carbon monoxide, formate, formic acid, nothing. Only carbon dioxide we have been able to detect in the gas GC or headspace GC. However, this benzoquinone actually kind of gave us some hints that probably we have generated hydroxycarbonyl radical. To detect it or to prove it in a better way, so we actually communicated with Marina Benatti group, which is very also famous for EPR spectroscopy in Göttingen. So she works in Max Planck Institute, and we tried to communicate with her, and then she said, yes, please work with my postdoc. And then we started to combining to get more information. What we have observed that when we don't have any light, any CO2, any catalyst, there was no signal. But as soon as we have started putting everything on, we started to get the signal, which is very similar like the hydroxycarbonyl radical, which has been proposed in this paper. The EPR signal was very similar. To further prove it, we also use 13 label carbon dioxide. So 13 CO2, and in EPR spectra, actually, if you have 13 CO2, all of your peak actually will be farther splitted. And this is what you can see, that all of your peaks are farther splitted under the EPR spectroscopy. And that was the clear proof that the CO2 has been converted to the hydroxycarbonyl radical, and then this hydroxycarbonyl radical was playing the role for the dehydrogenation reaction. So what is the overall picture? The overall picture is here. The right part, I have already explained to you that DBN was kind of playing the role to activate carbon dioxide, and it was releasing this hydroxycarbonyl radical. What happened to the left? So this is our photocatalyst. It was excited. The excited state catalyst was reacting with the amino group, our starting material. It generated this amino radical cation. Finally, in the presence of DBN as well, it releases H plus in the system. So it ends up to this carbon-centered radical. This radical then picks up the oxygen radical from sulfoxide or DMSO. So it generates this oxo-radical species. Finally, this oxo-radical compounds picks up this hydroxycarbonyl radical to reach in that stage. And I told you earlier as well, if we can reach to this stage, it won't be difficult to get the dehydrogenated product. And exactly, it's similar that as soon as we have reached there, the dehydrogenation became much more facile, much more simpler. So this is overall CO2 promoted chemistry. However, before closing my talk, I would also like to show you some of other parts of our chemistry, very short overview. So we are also working utilization of oxygen molecule, as Carmen told, that we are involved in the transformation of small molecule activation and their application as well. So the principle is very similar. We have the photocatalyst. We want to excite it to the excited state, and then we generate the radical anion from the system. This radical anion should be able to activate oxygen molecule to generate the superoxide radical anion. Many of the cases we have also seen the formation of singlet oxygen via energy transfer rather than this pathway. However, this singlet oxygen and superoxide radical anion we wanted to utilize via this radical cation from the organic molecule. And by that way, actually, we can transfer different amine moiety one step to the amide via late stage functionalization. We can also do non-activated oxidation of hydroxy compounds. Particularly, you can apply this chemistry to steroid molecule, which is very challenging. And we have been able to achieve this chemistry in the presence of metal-free catalyst. You can also do some de-aromatization of your indole or pyrrole type structures. And you can get some isatine or imide type structures directly utilizing metal-free strategies. Not only that, you can also utilize simple carbonyl compounds for the transformation of Diels-Alder type cycloaddition. Not only Diels-Alder, you can also do Aja-Diels-Alder reaction in your system. Additionally, you can also do some hydroxylation, selective CH1 hydroxylation reaction via metal-free catalysis. And at the time, I should also mention that we are not only doing with a homogeneous catalyst, we are also working on the development of heterogeneous, metal-free heterogeneous catalyst, and this is one of the example of this utilization of metal-free heterogeneous catalyst for the hydroxylation reactions. In the lab, except these things, we are also involved some plastic depolymerization, hydrogen peroxide synthesis, small molecule transformation, as well as CO2 transformation to small molecules. With these things, I think it's almost time to conclude my talk. So it's very clear, I hope, that we have been involved for the transformation in sustainable chemistry in both in the, let's say, for fine chemical as well as fuel type molecules. So we would like to incorporate more towards a renewable energy driven chemistry. I guess it's not only us, all of us, all the chemists, we want to provide a robust methodologies, and you guys already have seen it from Arjan's chemistry that catalysis, we need to provide a robust catalyst to provide robustness, selectivity we need it. This is what is very important in organic synthesis. We are also believing on natural intelligence-based prediction. Please don't get me wrong that I don't believe artificial intelligence. Yes, I do like that, but we should not forget that artificial intelligence can only give you some hints, but at the end, you need to make it, you need to prove it in your lab. So this is very important. So with these things, actually, I try to combine all of these things together. So we try to work in the lab to provide all this strategy, very similar like Arjan, what he has shown, that we need to address these challenges, how we can utilize carbon dioxide in the chemistry, how we can utilize CO2 to get some new molecules. The conclusive message is very clear that by doing this way, we cannot completely, I would say, decrease the emission of CO2 in the atmosphere. But in the other way, what we can provide kind of a sustainable strategy for the synthesis of organic molecules, an alternative strategy where you don't need to use any toxic chemicals. And those toxic chemicals you can avoid by using CO2. If you are very interested to read more about CO2 chemistry, so we have edited one book with the CO2 as a building block. I have many, I would say, intriguing contributor. Particularly, I should mention Arjan. He has written about substrate-driven CO2 fixation. Carmen about iron catalysis for CO2 fixation. Marcela Boncheos, she has also mentioned electrochemical carboxylation reactions. So I am thankful to all of the contributors in that book. If you are interested to know more about CO2 chemistry application in organic synthesis, I will particularly encourage all of you. Now, I will actually show you the most important slide of my whole lecture. So obviously the whole chemistry I haven't done, so probably my contribution is zero. They are the real hero. They are the pillar of the group. I'm just a Flipkart delivery boy who is just presenting their whole chemistry, combining their chemistry and sharing with all of you. So I'm particularly also thankful very much to all of my young members. Thanks to all the funding agency for funding to hire all these people. So before closing my lecture, actually, I heard that Luigi has been vaccinated, Carmen has been vaccinated, and I guess many of our Italian colleagues already have been vaccinated, those who are working in the teaching sector. However, in Belgium, this procedure is still not occurring. So I'm still believing on the artificial intelligence level vaccination. I hope that I get vaccinated very soon. I also encourage all of you to get vaccinated so that we all can become normal. We can come back to the normal stage. But please don't forget that as soon as there will be a normal situation, there will be a dramatic change in all over the world. With all these things, I would like to thank you for your kind attention. Once again, thanks Luigi, thanks Carmen for your kind invitation. Thanks to all the Italian colleagues for listening my talk. Thank you very much.
Thank you very much, Shoubhik, so for your very nice presentation. So you have gave us an idea that how to use CO2 in a different way. So like a catalyst, like an organic, non-toxic catalyst. So the green content of your contribution is not in the sequestration of CO2, but in the use of CO2 as catalyst, so as a non-toxic molecule instead of metal catalyst and so on. So I have, if there are no questions from the chat, I have a small question. So in the use of CO2 as catalyst, so for example, you showed the first effort without the photoactivation of CO2 in the dehydrogenation reaction. Did you have some example of reaction in which it's possible to modulate the which kind of product do you obtain using the modulating the pressure of CO2? Does the CO2 pressure plays a role in some of the reaction that you showed?
Yeah, Carmen, thank you very much for this question. To be honest, we have checked that with CO2 pressure, and we could not have been able to improve the yield. In some of the cases, for say the benzylic amino compounds, which we had the model substrates, so without in the atmospheric pressure, we had, let's say, 22%. With putting, let's say, 10 bar, we have been able to get, let's say, 25, 26, so which is nothing. So there was not enough, I would say, improvement utilizing CO2 or high pressure of CO2.
Okay. So if there are no, so please, Arjan.
Thank you. You can hear me, Shoubhik?
Yeah, Arjan, please.
Okay. So first of all, thank you very much for your presentation. I really liked it, and what I most liked about it is the original character of it, because coming from the let's say field of CO2 catalysis, there is a lot of chemistry that looks very much alike, and it's beautiful chemistry still. But I like you know, every now and then when there is somebody bringing new fire to the field. So maybe I can put it like that. And so it's just a couple of words of my appreciation for your work. Second, I need to know, you know, based on this picture, where you get your vaccine. So yeah, if you can, you know, give me an address where to pick up that vaccine, I would be extremely grateful. But that, of course, is nothing scientific. My scientific question is related to the photochemistry, which I obviously also very much like. So one general problem, of course, in photocatalysis is scale up. I mean, not for everyone, but let's say for most of the people it is. So you have, as we probably have as well, you know, similar kind of photoreactors. And what we have noticed that in most of our photocatalysis reactions, the you know, creating the photons is actually kinetically limiting. Yes. And that means that if you want to scale up, you need to be able to of course, address that issue. And so from your point of view, what would be the best way to scale up? Would you choose, let's say, a linear type of operation, or would you choose maybe a parallel type of operation? And maybe you know what I'm referring to, because also at Merck, or Merck, as they say in the United States, I think they are operating parallel photoreactors in a way, you know, as a way to scale up. Yeah. So, what is your view on that?
So I think this photoreactor actually the best solution at this moment. Yeah. So there is no doubt. And in fact, in our lab we have also built up. So this is ongoing now. This photoreactor is also working quite well. This linear type photoreactor, which is working quite well. So at the moment, and to be honest, there are some other companies. So in Belgium, actually, there is, I cannot exactly remember the name, but if you are interested, I can later send you. So they have one particular reactor, which the company is with in combination with Ajinomoto, if I can recall. So this company, they have designed a particular reactor. And with that, actually, you not only can do with homogeneous, you can do equal success rate, the heterogeneous photocatalyst. And they have told me when we had the initial discussion that they also have been able to get, let's say, 1 kg scale in a very smooth way. So obviously, they can scale it up further. This is what they told me. So with their strategy, actually, nowadays, we are working on how to build up one new photoreactor in our lab. So looks like for the preliminary things, it looks fine, but still we are in the, I would say, very primitive age. So we need to further build this strategy or further modulate how much scale up we can go further. So far it looks fine, and I agree with you that photocatalysis has the main drawback is the scale up. However, with the new advent of all this flow photoreactor, flow photocatalytic system, I think that problem we can definitely remove. The good point of photocatalysis, so often people mix it up that electrocatalysis is nice because you can scale up. Yes, it's true. But what we cannot kind of predict in electrocatalysis is kind of selectivity. It's still, I think, a black box. With photocatalysis, at least we can predict the selectivity, that which photocatalyst should work. At least it can show some reactivity. Here, actually, I'd mention that this is the only problem, but that problem can be solved using flow system.
Yeah, and I was thinking exactly along those lines, that photo flow catalysis could be a very, very useful approach.
Exactly. And I think this is going to become the future strategy.
Great, thank you.
Thank you, Shoubhik. We have one more question from Giulia Licini. Yeah. So please, Giulia.
Yeah. Okay. Thank you very much. Thank you very much for your talk. I really enjoy it. My question is related to the first part, and is somehow my concern, but in okay, DMSO is in principle your oxygen transfer reagent. Did you try anything different? Because of course, dimethyl sulfide is not very nice smell things, and so now it may be other species that can be also. Let's say, is more easy to recover and in case reoxidize and so on. Yeah, you do try an oxide, I don't know, other species that can be effective as well in your process.
Yeah. Thanks for this question. So we tried actually. For say, if you think about Mitsunobu reaction, one of the nicest example actually. So we are trying to achieve this Mitsunobu, CO2 catalyzed Mitsunobu reaction so that we avoid DMSO. The main problem is that we need the CO2 solubility in our system. And you know, as an organic solvent, DMSO is one of the very popular for CO2 solubility.
Yeah, sure.
And then again, there will be a competition. And at the moment, this part is not clear, like how much nucleophilicity is required for this system. Because if it is too nucleophilic, we have seen that it doesn't work. Although DMSO is not a super nucleophilic, it's a very mild nucleophilic reagent, very mild, but that works fantastically in the system. So this understanding we need to know a bit more carefully. I agree.
Okay, thank you.
So thank you very much. I would like to thank our speakers and really hoping that next time we meet, it will be in the life before COVID-19 because it's time to go back to the normal life. So, but now I leave the chair to Chiara Samori to present the contribution from the oral communication. Thank you.
Yeah, thank you, Carmen.
Thank you.
Thank you, Carmen, and thank you, both of you, Arjan and Shoubhik. And let's start the second part of the workshop with a short presentation by three authors. The first one is Ruggero Bonetti from the University of Padova. Ruggero, are you here?
Yes, indeed. Can you hear me?
Yes, we can hear you. And his talk is going to talk about molecular catalysis of the electrochemical reduction of CO2 by an iron 1 Schiff base complex.
Okay. I think you should be able to see my screen.
Yes.
Okay. So
please.
Okay, I will start now. So yes. Okay. Good afternoon. My talk will be, in fact, about this kind of catalysis that is a bit different from the strategies that have been discussed by our main speakers today. And actually, the electrocatalysis for the activation of CO2 is basically the second strategy that Professor Kleij discussed this afternoon. in which we employ electrical energy from possible renewable source, and we employ this energy to transform CO2 into useful chemicals, especially in the case that we are treating today, carbon monoxide. Of course, CO2 is inert, so transition metal catalysis is needed in this sort of process. And focusing on molecular catalysts, we have a plethora of transition metals, especially iron catalysis, in which iron is the most abundant and cheapest transition metal. So among these, the best performing catalysts are iron porphyrins, but also other classes of catalysts have been found and discussed in the literature. Today I will present a new poorly studied class of catalysts, the shift-based complexes, with the forerunner being the iron silophane of the silent type ligand. So, of course, being this kind of compound an electrocatalyst, I will have to show some cyclic voltammograms to describe its electrochemical properties. So, first, we have the CV here, the CV trace in an inert atmosphere. And what we can extract from this plot is that the iron is firstly reduced to iron 2, and then at minus 2.0 volts versus ferrocene, we convert it to the iron 1 species. And then as soon as we bubble CO2 into the electrochemical cell, we can record the change in the electrochemical properties that display themselves as an increase in the current associated with the generation of the iron 1 species. We can attribute these changing properties in observation to a reactivity involving the iron 1 species with CO2 that we had introduced in the system. So to further characterize what happens at the level of this redox transformation, we decided to generate in bulk the iron 1 active species by electrolysis, and then upon removing the applied potential, we decided to characterize it by spectroscopy and also to probe its reactivity with carbon dioxide. So we have here the iron 1 complex. We can see its picture inside the electrochemical cell once it was generated. And then upon introducing carbon dioxide in the cell, we can see this stark change in color that also translates in a change in spectral properties. And this change in spectral properties and also in color was attributed to the reaction between iron 1 that becomes oxidized and CO2 that becomes reduced contextually. So, of course, in order to determine what happens at the level of intimistic knowledge during this transformation, sort of to detect the intermediates that are involved. And we chose spectroelectrochemistry. Spectroelectrochemistry is a technique in which an electrochemical experiment is coupled to spectroscopy so that we can follow the spectral changes in the optical and electrochemical cell upon application of an electrochemical potential that induces redox chemical transformations. So in our case, we chose infrared absorption spectroelectrochemistry, and we actually recorded and detected the set of signals that arises upon electrolysis time, that we attributed the stretching of a carbon monoxide molecule coordinated to the iron center. So intermediate. This sort of intermediates is most often encountered in a reaction involving the production of carbon monoxide from the reduction of carbon dioxide. So, up to this point, we create electrochemically the iron 1 intermediate, and that this intermediate is reactive towards CO2. Furthermore, we have demonstrated that the sustained electrolysis of our catalyst and carbon dioxide produces an iron carbonyl intermediate. Therefore, to understand whether this behavior is really catalytic is whether carbon monoxide is released
Ruggero, ci senti? Scusa?
Ruggero, hai tolto l'audio. Se spegni la telecamera e rimetti l'audio.
Yes, sorry. I think I had some issues with my internet connection, and I'm sorry about this.
Navale ha detto che tra una 20.
Togli la videocamera.
Ruggero, prova a ricondividere lo schermo e a spegnere la videocamera.
Ma l'ho tolta?
Sì, ora sì, ma non vediamo il tuo schermo condiviso.
Sì, sì. Okay. Can you also hear me? Okay. Non capisco perché è successa questa cosa, però. Can you hear my voice? Oh. No.
Ruggero, scusami, mi senti?
Yes, I can. Sì, la sento. Sì.
Ok, proviamo a passare allo speaker successivo e magari se riesci ad aggiustare i problemi di connessione.
Mi dispiace.
Quindi Alessandro, sei qui?
Sì, eccomi.
Ok. So next move to the second speaker of this session, Alessandro Cerveri from University of Bologna, and he's going to speak about an anti-selective CO2 fixation via nickel catalyzed defunctionalization of alkenes. Please, Alessandro.
Thank you. Good afternoon to everyone. I'm Alessandro Cerveri and I third year PhD from University of Bologna in the laboratory of Professor Marco Bandini. I want to thank the organizer and the scientific committee for giving me this opportunity to show you my recent results about the anti-selective carbon dioxide fixation under nickel catalysis. So, chiral carboxylic acids are widespread in biomedicinal chemistry, and they often show a very high molecular complexity. We can think to synthesize this kind of compounds by classic approaches like conjugated additions or using the known enolate chemistry. But unfortunately, both of these well-known process methodologies are very limited, particularly when we are talking about this kind of products being a quaternary sterogenic center in the beta position of the carboxylic acid. Moreover, they will often need chiral auxiliaries or directing group and the protection of the carboxylic moiety. So we thought about a new disconnection, which actually give access to the system of the intramolecular olefin difunctionalization. So by using nickel catalysis, with this system, we hope to get a high selectivity in all the cases, so regio, chemo, and enantioselectivity. without using extra auxiliaries or groups. And since we are using carbon dioxide as a C1 synton, we will get directly the free carboxylic acid. So in nickel catalysis, this approach is also known as reductive coupling, and so we can, by choosing the appropriate starting material, we can obtain this intermediate by cascade oxidative addition and olefin insertion, and finally this intermediate can be reduced by one electron to this alkyl nickel 1 species, which can further react with a second electrophile to give the difunctionalized product. This approach has been explored from some groups recently, and they showed this reductive coupling with some of the most common electrophiles in the organic synthesis. So our purpose was to develop a similar system, able to catch the way less activated carbon dioxide to produce those kind of dihydrobenzo-fused heterocycles bearing a quaternary estrogenic center and a carboxylic acid moiety. We optimized the reaction conditions using VPY as a ligand, and then we moved on an anti-selective version of this reaction. We immediately observed that only oxazoline-based ligands, which are easily obtained from a natural amino acid, can actually perform during the reaction, and among them only the pioxazoline series, particularly the terbutyl substituted one, give a good result. Interestingly, the analog of the best ligand being a CF3 unit, so it's a more electron poor version of this ligand, gave very disappointing results. So we thought that the electronic properties of the ligand plays a very important role on the desired transformation. So we test the more electron-rich version of these ligands, which are pi-imidazoline, and finally we found our best conditions by employing L13 under nickel bromide catalysis. Also synthesized a nearly stable complex with this ligand, which has been fully characterized by X-ray spectroscopy in collaboration with Professor Magda Modari. Also, employing this catalyst in our process give comparable results to the in situ approach, even by lowering the catalytic amount to 5 mol%. Here are summarized just some simple control experiments. The more important are that in absence of trimethylsilyl chloride, we get no formation of the desired product. This could be explained by a cooperative action of the trimethylsilyl chloride in the reduction of the nickel with the zinc. More interestingly is the effect of the temperature on the system. So when we hike the temperature to 60 degrees, we obtain only a small amount of the desired carboxylic acid, and we observe the formation of many different byproducts. So we have a complete loss of selectivity. Differently, if we run the reaction at 0 degrees, we still obtain a lower yield, but almost all the remaining starting material has been converted to this benzoic acid. This actually could only derive from this aryl nickel 1 species, which can come from a precocious reduction of the aryl nickel 2. So this led us to suppose that this intermediate is a common intermediate in the formation both of the carboxylic of the benzoic acid and our desired carboxylic acid. We studied the scope using the preformed catalyst, and initially we just shown that also aryl bromide can perform in the reaction, but giving a lower yield. Our acid, we then converted it in the corresponding para-bromophenylamide, from which we obtained the single crystal X-ray to confirm the absolute configuration. We also shown that it's possible to synthesize the fully labeled product by using carbon-13 CO2, and this could be very useful for pharmaceutical pharmacodynamic studies, also maybe with carbon-14 CO2. For what regards the substitution of on the Fenner ring, also with more complex and labile functional groups, we observed in general a very good tolerance, and both the yield and the anti-selectivity are kept similar to our model substrate. We then also test the tolerance to the bulk substitution, both on the alkene moiety and in ortho position to the oxygen of the phenol, and even using coordinating groups, the sterical outcome is almost untouched. Unfortunately, the nitrogen-based analogs were not that suitable for this transformation, and we could obtain only those products only with moderate yields and non-selectivity. While when we used the fully aliphatic tethering unit, the corresponding dihydrobenzoindane, we obtained it with excellent anti-selectivity. So then we moved on study the mechanism, both on experimentally and computationally in collaboration with Professor Carlos Silva Lopez. We know that the catalytic species in this system is a one-to-one complex nickel ligand from nonlinear effect experiments. So this complex undergoes two oxidative addition on the aryl iodide to generate this aryl nickel 2 complex. Here, calculation showed a loss of iodine to favor the complexation of the double bond to the nickel and promote the stereoselective cyclization. A fast calculation on the energy barrier for the carboxylation of this intermediate showed that this could not happen in our reaction conditions. So this intermediate needs to be reduced by 1 electron from zinc, and finally can insert on the carbon dioxide. So a second reduction from the zinc generate back the nickel catalyst and give the final product as a zinc carboxylate. We also wanted to investigate more on the formation of the various byproducts, and two of the most common are the 3,3 sigmatropic rearrangement and the dimerization. Actually, those two byproducts are very easily rationalized, and they both comes from a nickel 0, nickel 2 catalytic cycle. But when we observed how the benzoic acid is formed, what we found is that firstly, the reduction from the aryl nickel 2 to this aryl nickel 1 is actually a very acceptable energy barrier. More interestingly, the carboxylation and the insertion on the double bond has almost the same energy. So that could explain both the formation of this product and also the loss of selectivity when we run the reaction at 0 degrees. And moreover, it could suggest that in this precise mechanism, we would have an anti-selective radical Heck coupling. So the insertion on the olefin will be operated by a nickel 1 species instead of a normal nickel 2 pathway. Moreover, anyway, this path, considering all the observation, looks more plausible than the previous reported. So in conclusion, we developed a new catalytic system which can able to synthesize carboxylic acid bearing quaternary stereogenic center and high molecular complexity. The reaction has a very mild conditions and shows a good generality. And the experimental and computational investigation gives a new interesting point of view on the reactivity of nickel towards olefins in general. So thank you all for your kind attention.
Thank you, Alessandro, for your presentation. Very interesting. Any question? Okay, so it seems no question for you, Alessandro. So I would like to thank you again for your presentation. And now we can, we can ask Fatima. If you are ready, Fatima, for your presentation, we can start with you.
Yes.
I apologize if I pronounce in the wrong way your name.
No, it's fine. It's fine. Okay.
Okay, let me introduce you. The next speaker is Fatima Niknam from the University of Salerno, and the title of her presentation is Co-polymerization of CO2 with epoxide by oxo-type chromium-3 catalysis. So please, Fatima.
Okay, thank you very much. I'm going to share my presentation. Can you see my presentation?
Yes.
Okay. Hello and good afternoon to everyone. It's very nice to meet all of you, dear professors and dear colleagues. And first of all, I would like to thank Società Chimica Italiana to give me this opportunity to talk about my recent activities. I'm Fatima Niknam. I'm from Iran, and I'm the first year PhD student at Department of Chemistry and Biology at University of Salerno, and I'm doing my PhD project under supervision of Professor Carmine Cappacchione. Okay. Besides environmental and energetic issues of carbon dioxide, it can be considered as resource. Nowadays, the strategy of using carbon dioxide as available, inexpensive, and non-toxic C1 building block is an efficient way to produce valuable fuels, chemicals, and materials. Of all the available methods for using carbon dioxide, its reaction with epoxide, which are thermodynamic unstable molecules with effective catalytic systems, has been attract attention because this strategy can overcome the thermodynamic stability and kinetic inertness of carbon dioxide molecule. Of course, the outcome of this type of reactions is valuable products such as cyclic organic carbonates or aliphatic polycarbonates. A large number of homogeneous catalysts have been reported for this type of reactions by different scientific groups, which are in combination with, most of them are based on transition metal complexes such as aluminium, iron, magnesium, chromium, and so on. And they are in combination with quaternary ammonium or phosphonium salts as co-catalysts. Here in this slide, I put some examples. The accepted mechanism for carbon dioxide epoxide coupling is accompanied with coordination of epoxides with Lewis acidic metal centers to produce activated species, and then a reaction of these activated species with nucleophilic co-catalyst to produce metalloalkylate species, and then following the CO2 insertion with into the metal oxygen bond, the carbonate will be produced. And in the following, we have three different options. By ring closure, the cyclic organic carbonates will be produced, and by alternate CO2 and epoxide, we have polycarbonates, and by 2 consecutive insertion of epoxide in the polymer change, we have polycarbonates with ether-polyether linkage. Here we reported a synthesis of new chromium-3 complexes based on bis CO2 ligands, the so-called OSO ligands, by adding 2 equivalent of sodium hydride in dried THF, and then adding 1 equivalent of chromium chloride at room temperature. The pro-ligands were synthesized according to the literature. Our OSO-type chromium complexes were characterized by a molded tough mass analysis. For example, for complex 1, we observed 2 signals which were assigned to the complex 1 minus THF and complex 1 minus THF plus hydrogen with positive charge. And both of these signals were supported by theoretical spectrum also. And also for complex 2, also we observed signals related to complex 2 minus THF with positive charge. And also for complex 3, also the signals were assigned to complex 3 minus THF plus water with positive charge. Again, these 2 complexes also were supported by theoretical spectrum. In the following investigation of the catalytic activity of our catalyst were done by using propylene oxide. Here I put the data in this table. We try to investigate the catalytic activity of catalyst 1 to 3 in different conditions. We started with 20 bar of the pressure of CO2 and 24 hours for the time of the reaction. And also the ratio of co-catalyst to catalyst was 0.5, and the ratio of catalyst to epoxide was 0.1 mole per cent. According to this reaction at fixed temperature that was 45 Celsius degree, the conversion for catalyst 1 was better in respect to catalyst 2 and catalyst 3, and also the percentage of polycarbonate produced during this reaction was better for catalyst 1. We also investigate the effect of increasing time and also increasing the pressure of CO2 for our catalyst, catalyst 1, at a fixed temperature, which was 45 Celsius degree. So the result didn't show significant changes. We choose our catalyst 1 as the best catalyst during the reaction with propylene oxide and carbon dioxide. We tried to find the best conditions in respect to temperature. So we investigate the catalytic activity of catalyst 1 in comparison respect to temperatures, which was 30, 45, and 50 and 60. The data are shown here in this table, and also the diagram is also here. So the best condition was in tray 2, which was temperature was 45 Celsius degree. With the polycarbonate percent of 88, and the percentage of conversion was 44. And I would like to say that the method for calculate the conversion were based on using hydrogen NMR spectroscopy and using mesitylene as internal standard. The reaction of carbon dioxide with cyclohexane oxide led to formation of exclusive formation of almost perfect polycyclohexane carbonate. And we try to increase the percentage of our polycarbonate. So we increase the temperature from 45 Celsius to 100 Celsius. From 45 to 60, the percentage of conversion was increased, but from 60 to 80 and also 80 to 100, the we didn't see significant changes in the conversion. Here I put as an example the hydrogen NMR spectrum of our polycyclohexane carbonate and the way that we calculate the percentage of conversion. For example, in this case, we can assign to hydrogen, and then according to the formula, we can calculate the percentage of conversion. But the point is that in this case, I mean, polycyclohexane carbonate, the signals that we assigned is similar or almost similar to the cis-cyclohexane carbonate. So we used carbon NMR spectroscopy for the product, so we can confirm that our polymer is produced. And according to this spectrum, we get also some other data about the arrangement of our polymer. In the case of hexane oxide, at optimized condition, which was 20 pressure of CO2 and 45 Celsius degree, and the ratio of co-catalyst to co-catalyst 0.5, we get 80% of polycarbonate with 30% of conversion. But by increasing temperature, the results was changed. We have just cyclic carbonate, the conversion was 85%, and it shows that this product is our thermodynamic product. In this table, I put the data related to copolymerization of carbon dioxide with different epoxides, from styrene oxide, epichlorohydrin, hexane oxide, 1 and 2 dodecan, furfuryl ether, and allyl ether. We tried, I put the best data, and we with high percentage of our cyclic carbonates and conversion in this scheme. And for example, I can talk about each samples a bit. For example, in the styrene oxide, by increasing the temperature from 45 to 80, the conversion was increased to 46%. And also in the epichlorohydrin case, by increasing again temperature, we saw the increasing in the conversion, and by using excuse me. And by in the case of hexane oxide, by changing the co-catalyst from PP and Cl to TBOB with the ratio of 5, we got 50% of conversion. And also in the case of the 1 and 2 epoxy dodecan, which is similar to hexane oxide, we tried to have the same conditions, but the conversion was decreased, which is reasonable, maybe because of the line change made its ring opening difficult in comparison of hexane oxide. And also the best results for furfuryl ether was using 5 ratio of TBOB, which was 90% of conversion, and also another epoxide was allyl ether, which was similar to furfuryl ether. So we used the same conditions, but we have 73% of conversion. Which is maybe related to the difference of properties of furfuryl ether in comparison of allyl ether respect to its furan ring, because generally withdrawing groups in the epoxides cause decreasing durability to coordinate with metal centers that cause have a higher activation energy. And also we try to find the TG for our polycyclohexane carbonate. The data was agreement with the reported data in the literature, and also in the case of polypropylene carbonate. Here in this slide, I just summarize the data. We synthesize a series of also type of complexes and characterize them. And also we investigated the copolymerization of this type of catalyst with different epoxide and carbon dioxide. In the case of cyclohexane oxide, we have just polycyclohexane carbonate, and also a series of perfect cyclic carbonate also were reported regarding the reaction of our catalyst with carbon dioxide. And also all of the products were fully characterized by hydrogen NMR spectroscopy, and in some cases by carbon NMR spectroscopy. Thank you very much for your attention. I would be happy to answer if there are some questions.
Thank you, Fatima, for your presentation. Any question? Okay, so it seems no question for you. Again, congratulations for your talk. And now we can ask Ruggero to show his presentation, and maybe you can start from the beginning. I cannot hear you.
Maybe it should be working now.
You can try to increase the volume, maybe.
Sorry. I'm trying to change my...
Se fosse possibile provare senza microfono, perché sospetto che il portatile potrebbe andare meglio. Se toglie le cuffie e il microfono delle cuffie direttamente quello del computer.
Ruggero, non ti sentiamo. Vuoi provare a sganciare le cuffie?
Guarda Ruggero, in alto a fianco alla telecamera ci sono i tre puntini. Se premi e provi le impostazioni può darsi che sono saltate le impostazioni del microfono.
Sa che...
Ruggero, non so se hai sentito in alto sulle impostazioni del microfono, sono quei tre puntini a fianco alla telecamera. Io proverei lì a vedere che microfono hai selezionato. In alto.
Sulla barra dello schermo.
Io non so se ci senti, Chiara, ma per in qualche modo capire se possiamo aiutarlo, perché sennò dovremmo in qualche modo prendere una decisione, non possiamo tenere le persone così tanto tempo. Quindi io non so se ci sente, perché... Grazie Giorgio. Giulia, allora io non so come procedere, però effettivamente Ruggero al momento non è connesso, no, è connesso, non ci sente per niente.
Ancora, è connesso, però non ci sente, credo. Sto cercando di comunicare con qualcun altro che è lì, ma adesso vediamo se compaiono, che avevano cambiato il
Diciamo che questa
computer.
organizzazione online effettivamente non si può nemmeno fare da supporto tecnico se non ci sente.
Esatto, aspetta. No, dice che lui ci
Forse
sente, ma
ecco,
noi non lo sentiamo. Almeno adesso lo
però io
vediamo.
dicevo, Ruggero, se non ci sente, se ci sente ma non lo sentiamo, potrebbe andare sulle impostazioni in alto, a fianco alla telecamera, sono i tre puntini per le impostazioni, impostazione dispositivo, e verificare quale microfono tu hai a disposizione.
Prova
E
a
in
parlare
caso
perché
togliere tutto, togliere le cuffie, tutto per lasciare il microfono del computer. Impostazioni dispositivo, a quel punto c'è l'altoparlante e il microfono selezionato. Se ci scrivi sulla chat qual è la conclusione,
Ruggero, ci senti? Vabbè, pazienza, Ruggero, non... c'è un caso di incomunicabilità. Pazienza, mi spiace, dai. Cioè, comunque il poster e la presentazione, cosa dite? Credo che non so, cioè, sono problemi della connessione, si vede. Perché adesso si vede bene, ma non ti sentiamo.
ma se ci scrivi, scusami, scrivi nella chat, ti ho appena scritto nella chat, hai trovato le impostazioni? E allora se non...
C'è qualche problema? C'è qualche problema con la connessione, non so se Andrea può... Ma strano, non so. Pazienza, ma adesso mi pare che non possiamo... Non ne veniamo fuori.
Va bene.
Ruggero, abbandoniamo? Diamo forfè? Ok, mi spiace.
Mi dispiace, Ruggero.
Sarà...
Chiara,
ok, potete...
Non ha trovato l'impostazione, ma basta scrivere, no? Vabbè, comunque, andiamo. Penso che non riescono a comunicare nemmeno sulla chat, quindi diciamo nemmeno, cioè, quindi è proprio difficile. Noi possiamo altro che ringraziare di nuovo tutti, grazie Chiara per aver sostenuto questa sessione difficile e grazie a tutti per aver partecipato. I don't know if Arjan and Shoubhik, they are still connected. I just want to thank their participation again, their availability to give lectures, and my best regards. Hope to see you again as soon as possible in person.
Yeah, Luigi, thank you very much for your kind invitation. Thank you to Carmen. Thanks to all the colleagues who are involved organizing this event. Thank you very much.
Thank you.
Thank you.
Yeah.
Good evening.
Bye bye.
Thank you all.
Shoubhik.
Bye bye.
Ciao.
Thank you very much. Bye.
Ciao.